Hello there, and welcome to Science for Sleep, where curiosity settles in, the pace slows down, and science is allowed to unfold without urgency. This is a place for wandering ideas, gentle explanations, and questions that do not demand immediate answers. Wherever you happen to be listening from tonight, whether the room around you is bright or dim, familiar or unfamiliar, you're invited to let the day loosen its grip just a little. There's nowhere you need to go next, nothing pressing that needs solving right now. Only a quiet journey inward, guided by one of the smallest and strangest frontiers science has ever tried to describe. Tonight, we're going to drift toward a place that does not feel small in the ordinary sense. Not like a grain of sand or a drop of water or even an atom. This is a scale so far removed from everyday experience that language itself starts to strain under the weight of describing it. A place where the usual ideas about size, force, space, and even time begin to behave differently, sometimes uncomfortably so. Physicists have a name for this boundary, a kind of conceptual shoreline where our best theories stop agreeing with one another. It is often called the Planck scale, and within it lives something we loosely refer to as the Planck force. Before we move any further, it might be worth pausing to notice where you are right now. Are you listening late at night, when the world outside has gone quiet and even familiar objects feel slightly different? Or perhaps it is earlier, with the day still unfolding, but you have chosen to slow down anyway. What place are you in, and what time is it there? These small anchors to the present moment matter, especially when we're about to talk about scales where the idea of a moment becomes difficult to define. If you find this kind of exploration calming, or if the steady pace helps your thoughts ease out of their usual loops, you're always welcome to show your support by liking the video or subscribing to the channel. It helps keep this quiet corner of science available for others who may also be looking for a gentler way to end or begin their day. There is no rush to do that now though. Nothing here is in a hurry. To begin, it helps to acknowledge just how comfortable our everyday sense of size really is. We live in a world measured in meters, minutes, and manageable forces. You can feel the weight of a cup in your hand. You can judge the distance across a room without thinking too hard about it. Gravity pulls you downward in a steady, predictable way. Even when we talk about very large things like mountains or planets, we are still extending familiar ideas outward. Bigger versions of what we already know. The same is true to a point when we talk about small things. We learn about cells, then molecules, then atoms. Each step downward feels impressive, but still manageable. An atom is tiny, but it exists in space. It has parts. It follows rules we can write down and test. Go smaller still to electrons and quarks, and things become stranger, but there is still a sense that we are describing objects, entities that live somewhere and do something. The Planck scale is different. It is not just smaller by a factor of 10 or even a trillion. It is smaller in a way that breaks the ladder we have been climbing. The Planck length, for example, is about 1.6 times 10 to the minus 35 meters. Writing that number down already feels abstract, but the real difficulty is not the size itself. It is the implication. At this scale, the very idea of distance starts to lose its usual meaning. The Planck force enters the picture when physicists try to combine several fundamental constants of nature into a single expression. These constants include the speed of light, the gravitational constant, and Planck's constant, which governs the behavior of quantum systems. When arranged in a certain way, they produce a force so large that it dwarfs anything we encounter elsewhere in physics. It is not a force we can generate, measure directly, or apply in an experiment. Instead, it represents a kind of upper limit, a boundary condition that tells us something important about how the universe holds itself together at its most extreme. Calling it a force can be misleading, and scientists know this. It does not behave like gravity pulling objects together, or electromagnetism pushing charges apart. The Planck force is more like a signpost. It marks the point where gravity, usually the weakest of the fundamental interactions, becomes as strong as the others. At everyday scales, gravity is gentle. You feel it as weight, as a steady pressure holding you to the ground. At the Planck scale, gravity is anything but gentle. To understand why this matters, it helps to think about how we normally describe the universe. Modern physics rests on two towering frameworks. One is quantum mechanics, which describes the behavior of particles and fields at very small scales. The other is general relativity, which describes gravity as the curvature of space and time at large scales. Both theories work astonishingly well in their respective domains. They predict experimental results with incredible precision. Satellites stay in orbit. Electronics function reliably. The equations do their jobs. The trouble starts when we ask what happens if we push both theories to their limits at the same time. What happens when something is extremely small and extremely massive, or when energy is packed into an incredibly tiny region of space? This is where the Planck scale appears, not because anyone went looking for it as a physical place, but because the mathematics insists on it. At these scales, quantum fluctuations in energy become so intense that they can significantly distort space itself. Space is no longer a smooth stage on which events play out. It becomes restless, uneven, and unstable. Time, which we usually treat as a steady backdrop, begins to wobble as well. The usual separation between cause and effect becomes harder to define. This is not because reality has stopped making sense, but because the tools we use to describe it are no longer adequate on their own. The Planck force is tied to this breakdown. It represents the scale at which attempting to confine energy any further would require forces so extreme that spacetime itself would respond dramatically. Instead of simply holding more energy, space might curve sharply, form horizons, or collapse into something like a microscopic black hole. The familiar idea of pushing harder stops working in the way we expect. It is important to say clearly that no one has ever observed the Planck scale directly. There is no microscope powerful enough, no particle accelerator large enough to probe distances that small. Even the most energetic collisions we can produce fall many orders of magnitude short. The Planck force is inferred, not measured. It emerges from equations that have proven reliable everywhere else, extended into a regime where we know they cannot all remain valid at the same time. This makes the Planck scale a strange kind of destination. It is a place we reach by reasoning rather than by travel, a boundary we infer because our maps start contradicting one another. In that sense, it is less like a hidden room waiting to be opened, and more like the edge of a fog where familiar landmarks fade from view. Despite this, physicists take the Planck scale very seriously, not because they believe it is the final word on reality, but because it tells us where our current understanding ends. The Planck force, in particular, suggests that there is a maximum stiffness to space-time, a limit to how violently it can be bent or stressed before something fundamentally different happens. That idea alone has deep implications for how the universe began, how black holes behave, and whether space and time are continuous or made of something more discrete. As you listen, it may help to let go of the urge to picture everything too clearly. The human mind is very good at imagining objects moving around in space. It is less good at imagining situations where space itself is uncertain. When explanations start to feel slippery, that is not a failure of attention. It is a sign that you're approaching a scale where intuition was never meant to function smoothly. Think about how different forces feel in everyday life. Gravity feels constant and reliable. You rarely notice it unless something changes, like stepping into an elevator or climbing a hill. Electromagnetism is more obvious when it acts, in the spark of static electricity or the glow of a screen. Strong and weak nuclear forces remain hidden inside atoms, quietly doing their work without calling attention to themselves. The Planck force does not belong to this list in the usual way. It is not something you feel or observe. It is a constructed quantity, one that tells us how intense interactions could become if all known forces were pushed to their theoretical extremes within the smallest possible region. In that sense, It is less a physical actor and more a statement about the structure of the universe. This can sound distant or abstract, but there is a calmness in recognizing limits. Just as there is a maximum speed at which information can travel, there appears to be a scale beyond which our usual descriptions of force and motion no longer apply. The universe, it seems, has built-in boundaries, not as walls, but as transitions from one way of behaving to another. You might notice that thinking about such extremes has a peculiar effect. On one hand, it can feel unsettling. The idea that space and time might break down challenges deeply held assumptions. On the other hand, it can be oddly reassuring. The same rules that govern the motion of galaxies also place limits on how wild things can get at the smallest scales. There is a kind of balance in that. As we ease further into this topic, it is worth remembering that the Planck scale is not where everything suddenly becomes chaotic without structure. Rather, it is where new kinds of structure may exist, ones we have not yet learned how to describe. Many theoretical frameworks attempt to do this. Some suggest that space is made of tiny, discrete units. Others propose networks, loops, or relationships that replace the idea of smooth geometry altogether. None of these ideas have been confirmed, and that uncertainty is part of the story. Physics at its edges is not a finished narrative. It is a collection of careful guesses, constrained by mathematics and consistency, waiting for evidence that may take generations to acquire. The Planck force sits quietly in the background of these efforts, a reminder that whatever theory comes next must respect the same fundamental limits. As your thoughts settle into this landscape of small scales and large questions, you do not need to hold on to every detail. The goal here is not mastery, but familiarity. Let the concepts pass by at a pace that feels comfortable. There is no test at the end, only a gradual easing into ideas that are vast in implication, even when they describe the unimaginably small. In a way, starting with the smallest place imaginable is an invitation to shift perspective. When the universe is viewed from its limits, everyday worries tend to soften around the edges. The precise mechanics of the Planck force may remain unresolved, but the act of considering them places us within a much larger story, one that continues unfolding whether we are awake to watch it or resting quietly as it moves along. There comes a point as we continue easing our way inward where the familiar idea of size begins to lose its grip. Not suddenly, not with a dramatic snap, but gradually, like a ruler that keeps stretching until the markings blur and the numbers no longer feel anchored to anything solid. Up to now, shrinking things down has felt manageable. You take an object, imagine it smaller, then smaller again. Even if the numbers become extreme, the mental process stays the same. But eventually, that process itself stops working. In everyday life, size is relational. A chair is larger than a book is larger than a coin is larger than a grain of sand. These comparisons rely on shared experience. You know what it means to hold these things, to move around them, to exist beside them. Even when science pushes beyond direct experience into the realm of cells and molecules, the language still leans on extension. A molecule is like a tiny cluster. An atom is like a miniature solar system, at least in the loosest metaphorical sense. The images are imperfect, but they give the mind something to rest on. As we move closer to the scales associated with the Planck force, those resting points disappear. The problem is not just that things are small, it is that the concept of small itself assumes a background that no longer behaves the way we expect. Size, as we usually understand it, requires space to be stable, smooth, and continuous. It assumes that distances can always be divided into smaller distances without changing their nature. At extreme scales, that assumption becomes questionable. Consider what it means to measure something. Measurement is an act of comparison. You place one thing against another and see how many times it fits. A ruler against a table, a clock against a duration. Even when the instruments become more sophisticated, the principle remains. Measurement depends on reference points that are themselves well defined. When physicists talk about lengths approaching the Planck scale, they are talking about distances so small that the very act of defining a reference point becomes problematic. At these scales, quantum mechanics refuses to stay quiet. Energy fluctuates even in what we would normally call empty space. These fluctuations are not just theoretical curiosities. They have measurable effects at larger scales, like subtle shifts in energy levels or tiny forces between objects placed very close together. But near the Planck length, these fluctuations become dominant. Space is no longer a calm backdrop. It is active, restless, and unpredictable. This is where size stops behaving like a simple number. You cannot point to a location and say it is precisely here, because here itself is smeared by uncertainty. Quantum mechanics tells us that the more precisely you try to pin down a position, the more energy you must concentrate. Gravity, described by general relativity, responds to energy by curving space. At small enough scales, these two effects collide. Trying to define a very small region requires so much energy that space itself reacts dramatically. The Planck force enters this discussion as a marker of that collision. It represents the scale at which gravitational effects become comparable to quantum effects within an extremely confined region. Beyond this point, adding more energy does not simply mean a stronger interaction. It means altering the structure of space itself in ways our current theories cannot fully reconcile. This leads to an uncomfortable but important realization. There may be a minimum meaningful length, not because reality refuses to be smaller, but because our concepts of distance and size lose coherence. Asking what happens below that scale may be like asking what lies north of the North Pole. The question assumes a framework that no longer applies. This idea runs counter to centuries of scientific habit. Physics has long thrived on the assumption that nature can be described at any scale, given sufficient precision. The notion that there could be a fundamental limit to divisibility challenges that tradition, yet the mathematics keeps pointing in the same direction. When fundamental constants are combined, they consistently produce the same scale, suggesting that this is not an artifact of a particular theory, but a feature of reality itself. It is tempting at this point to imagine the universe as pixelated, with space made up of tiny blocks that cannot be subdivided further. While this analogy can be useful, it also risks oversimplifying the situation. Pixels are static and well-defined. The structures proposed at these scales, if they exist at all, are likely far stranger. They may not resemble objects arranged in a grid. They may not even resemble things in the usual sense. One reason size becomes so slippery is that time is tangled up in the same problem. Distance and duration are linked through the speed of light. If there is a smallest meaningful length, there may also be a smallest meaningful interval of time. Near these limits, the usual sequence of events becomes harder to order. Cause and effect, which we rely on so heavily, may not behave in a clean, linear fashion. This does not mean that reality dissolves into chaos. It means that the categories we use to describe it need revision. Just as Newton's ideas about absolute space and time had to be replaced when experiments demanded greater accuracy, our current notions of size may be provisional, valid only within a certain range. It can be helpful to step back and notice how often this has happened before. At one time, atoms were thought to be indivisible. Their name even means uncuttable. Later, they were found to have internal structure. Then those structures were found to have deeper layers. Each time, the boundary moved. What makes the Planck scale different is that the boundary appears not because we found smaller parts, but because our methods of description stop agreeing with each other. The Planck force highlights this disagreement. It tells us that gravity, usually negligible in particle physics, cannot be ignored at sufficiently small scales. At the same time, quantum uncertainty prevents gravity from being treated as a smooth classical field. Each theory demands conditions that invalidate the other. Size, caught between them, becomes an unstable concept, When people first encounter this idea, there is often a sense of frustration. It feels like hitting a wall. But there is another way to see it. Instead of a wall, it may be a transition, a place where new kinds of description become necessary. After all, temperature is a useful concept at large scales, but meaningless when applied to a single molecule. That does not mean molecules are poorly understood. It means temperature emerges only when many of them act together. Size may work the same way. It may be an emergent property, meaningful only when space behaves classically. Below a certain scale, asking how big something is may not be the right question. The more appropriate questions might involve relationships, interactions, or patterns that do not translate neatly into distances. The Planck force, in this context, acts as a boundary between regimes. Above it, forces can be compared, measured, and applied without tearing the underlying framework. Below it, the framework itself becomes part of the interaction. Space is no longer just where things happen. It participates. As you take this in, it is okay if the ideas feel resistant. Human intuition evolved to handle mid-sized objects moving at modest speeds under gentle forces. It did not evolve to grasp regimes where energy, space, and time intertwine at extremes. The discomfort is not a sign of misunderstanding. It is a sign of proximity to the edge of familiar thinking. There is also something quietly humbling about this realization. No matter how advanced our instruments become, there may be aspects of reality that cannot be accessed by simply building smaller rulers or stronger microscopes. Progress in this domain may require entirely new ways of thinking, not just better tools. Physicists exploring these questions often rely on thought experiments rather than direct observation. They imagine confining energy to smaller and smaller regions, or probing space with ever-increasing precision, and then follow the consequences implied by known laws. Time and again, these thought experiments converge on the same conclusion. Push too far, and the concepts themselves start to unravel. This does not diminish the achievements of science. On the contrary, it highlights its honesty. Instead of pretending that answers exist just beyond our reach, the theories openly admit where they fail. The Planck scale is not a mystery because no one has tried to understand it. It is a mystery because understanding it requires something fundamentally new. As we remain with this idea a little longer, notice how it reframes the notion of the smallest place imaginable. It is not a tiny dot waiting to be zoomed in on. It is a threshold, a place where the question, how small, gives way to what kind of structure, what kind of relationship, what kind of description. The discussion naturally begins to lean toward measurement itself. How do we know when size stops making sense? What happens when the act of measuring changes what is being measured in unavoidable ways? At some point, after size itself begins to feel unreliable, attention naturally shifts to the tools we use to make sense of the world in the first place. Measurement sits quietly at the foundation of almost everything we call science. It feels neutral, objective, and dependable. You measure a length, a mass, a duration, and you get a number. That number may come with uncertainty, but the act itself feels straightforward. Yet the closer we drift toward the Planck scale, the more measurement stops being a passive act and starts becoming part of the problem. In ordinary situations, measuring something does not significantly alter the thing being measured. You can weigh a book without changing its contents. You can time a walk without affecting how long it takes. Even at microscopic scales, measurement feels manageable. A microscope illuminates a cell. A detector records a particle's path. There are complications, yes, but the basic idea remains intact. There is an object. There is an instrument. One reveals information about the other. Near the Planck scale, that separation breaks down. The difficulty is not technological in the usual sense. It is not simply that our instruments are not sensitive enough. The problem is deeper. The very principles that allow measurement to work start interfering with one another in unavoidable ways. To see why, it helps to consider what measurement actually requires. To measure a distance, you must define 2 points in space, and compare the separation between them. To define a point precisely, you need to localize something there, often by concentrating energy. Light is a common choice. You shine light. It interacts with what you are observing, and information returns to you. The shorter the wavelength of the light, the finer the detail you can resolve. This strategy works beautifully at human and atomic scales, but wavelength and energy are linked. Shorter wavelengths require higher energies. As you attempt to probe smaller and smaller distances, the energy involved in the measurement increases. Quantum mechanics insists on this relationship. It is not a matter of preference or design. It is built into the structure of the theory. Now gravity enters the scene. According to general relativity, energy and mass curve space-time. The more energy you concentrate in a region, the more strongly space responds. At everyday scales, this effect is negligible. A laser beam does not noticeably warp the room it passes through. But when the energies involved become extreme, curvature can no longer be ignored. The Planck scale marks the point where these two demands collide. To measure a distance that small, you would need so much energy packed into such a tiny region that gravity would respond violently. Instead of revealing finer detail, your measurement process would distort the very space you're trying to measure. In extreme cases, the energy density could be sufficient to form a microscopic black hole, hiding the region behind an event horizon and making measurement impossible in principle. This is not a practical limitation. It is not something that will be solved with better engineering. It is a conceptual limit. Measurement fails not because we are clumsy, but because the act of measuring triggers physical effects that undermine the goal. The Planck force plays a quiet but central role here. It represents the scale at which gravitational effects can no longer be treated as weak or ignorable during measurement. It signals that space-time itself resists being probed beyond a certain point, not actively, not with intention, but through the consistent application of its own rules. It is worth lingering on this idea because it runs against deeply ingrained assumptions. Science is often portrayed as an endless march toward finer resolution. Smaller particles, shorter timescales, higher energies, and for centuries that portrayal has been accurate. Each time a limit appeared, new methods found a way around it. But the Planck scale is different. It is not a wall erected by incomplete knowledge. It is a boundary implied by the very theories that have succeeded everywhere else. This realization changes how physicists think about what questions are meaningful. Asking what exists below the Planck length may be like asking for a measurement that cannot, even in principle, be performed. The universe does not provide an answer because the question itself presupposes a framework that no longer applies. That does not mean nothing exists there. It means existence may need to be described differently. Measurement as we know it depends on separation, comparison, and localization. If these concepts fail, then whatever underlies them cannot be accessed by the same methods. Uncertainty plays a central role in this breakdown. Quantum uncertainty is not about imperfect instruments or human error. It is a fundamental feature of nature. Certain pairs of properties cannot be known simultaneously with arbitrary precision. Position and momentum are the most famous example. The more precisely you know one, the less precisely you can know the other. At ordinary scales, this uncertainty is small enough to ignore. Objects have well-defined positions for all practical purposes. At extremely small scales, uncertainty becomes dominant. Attempts to reduce uncertainty in position require adding energy, which then increases uncertainty elsewhere and through gravity reshapes space-time itself. Measurement becomes self-defeating. Each attempt to sharpen the picture introduces new distortions. Instead of revealing a clearer image, you end up stirring the medium you're trying to observe. This has led some physicists to suggest that space-time itself may not be a fundamental entity but an emergent one. Just as temperature emerges from the collective motion of particles, space and time may emerge from deeper, non-spatial relationships. At large scales, these relationships average out into something smooth and continuous. At small scales, the underlying structure becomes apparent, and the familiar notions dissolve. If this is the case, then the Planck scale represents the resolution limit of spacetime itself. Not because reality ends there, but because spacetime stops being the appropriate language. Measurement, which relies on spacetime concepts, reaches the end of its usefulness. There is a subtle calmness in this perspective. It suggests that the universe is not withholding information out of secrecy or hostility. It simply operates according to rules that do not always align with our preferred methods of inquiry. Measurement works where it works, and stops where it stops. This also reshapes how physicists think about unification. The long-standing goal of uniting quantum mechanics and gravity is not just about combining equations. It is about finding a framework where measurement makes sense again at extreme scales. A theory where probing the smallest structures does not destroy the stage on which the probing occurs. Many approaches attempt this in different ways. Some redefine what it means to measure distance. Others replace space-time with networks, relationships, or algebraic structures that do not rely on geometry in the usual sense. In these frameworks, the Planck scale is not a smallest ruler mark, but a transition point between descriptions. As these ideas circulate, it becomes clear that the limits of measurement are not obstacles to be overcome, but clues. They tell us something profound about how reality is organized. They hint that the universe is not infinitely divisible in the way our intuition suggests, and that asking for ever finer detail eventually stops being meaningful. This realization can feel unsettling, especially in a culture that values precision and control. But it can also feel grounding. There is a sense of order in knowing that even the most fundamental theories impose limits, that there is a point beyond which the universe refuses to be interrogated in familiar ways. As you remain with this idea, notice how gently it shifts perspective. Measurement, once taken for granted, becomes an active participant in the story. The observer is no longer separate from the observed. The act of inquiry leaves an imprint. If measurement of distance fails at certain scales, what does that say about space as a physical entity? Is it smooth, as it appears, or does it have structure that only becomes apparent when measurement breaks down? As attention moves away from measurement itself and settles more firmly on what is being measured, space starts to look less like a quiet backdrop and more like an active participant. For most of human history, space was treated as something simple and dependable. It was the stage on which everything else happened, empty unless filled, passive unless acted upon. Even when physics became mathematical, that assumption largely stayed intact. Space was where objects existed. It did not have much to say about the events unfolding within it. That picture works extremely well at familiar scales. A room feels smooth and continuous. You can move your hand through the air without resistance. 2 points in space can be connected by a straight line, and that line behaves exactly as expected. Geometry applies cleanly. Distances add up. Angles behave themselves. Nothing about space feels fragmented or uncertain. Even when Einstein changed the story by linking space with time and allowing gravity to curve it, smoothness remained central. Space-time could bend, stretch, and warp, but it was still treated as a continuous fabric. You could zoom in as much as you liked, and the equations would continue to work. Curvature might increase, but there were no cracks, no grains, no sudden failures of definition. The trouble begins when we try to push that smooth picture into the extreme regime associated with the Planck scale. At those scales, the assumptions that keep space well behaved start to conflict with other parts of physics. The idea that space can be infinitely smooth and infinitely divisible begins to clash with quantum behavior in a way that cannot be ignored. One way to approach this is to think about what smoothness really means. When we say space is smooth, we mean that it can be described by continuous mathematics. You can take derivatives. You can define curvature at every point. You can talk about trajectories that change gradually rather than abruptly. Smoothness allows for predictability and coherence. It lets geometry do its work. Quantum mechanics, however, introduces an unavoidable jitter. Even in regions we would normally call empty, energy fluctuates. Fields are never perfectly still. Particles appear and disappear within the limits allowed by uncertainty. At large scales, these effects average out. Space looks calm because countless tiny disturbances cancel each other in a statistical sense. Near the Planck scale, that averaging breaks down. The fluctuations are no longer small compared to the scale being examined. They become comparable to it. Instead of ripples on a pond, you're dealing with something more like boiling water, where the surface itself is constantly breaking and reforming. In such a situation, describing space as smooth becomes increasingly strained. Gravity complicates this further. In general relativity, gravity is not a force acting within space. It is the geometry of space itself responding to energy and momentum. Where there is energy, space curves. Where energy changes, curvature changes. At ordinary scales, this response is gentle. Even massive objects like planets create curvature that is subtle enough to be approximated smoothly. At extremely small scales with extremely high energy densities, the response becomes violent. Tiny fluctuations in energy lead to significant changes in curvature. Space is no longer a stable canvas. It is dynamic, reactive, and restless. The notion of a fixed background dissolves. The Planck force is a useful marker in this discussion because it tells us how intense interactions would need to be for gravity to compete directly with other fundamental effects at very small scales. It signals the regime where space cannot be treated as an inert container. Instead, it becomes entangled with the processes taking place within it. This is where the idea of smooth space starts to fail, not as a convenience, but as a principle. If space is subject to quantum fluctuations, and if those fluctuations carry enough energy to significantly alter geometry, then space itself must fluctuate. The smooth curves of classical spacetime give way to something rougher, more irregular, and less easily described. Physicists sometimes refer to this as quantum foam, though the term can be misleading. Foam suggests bubbles, surfaces, and familiar textures. What is meant instead is a regime where geometry itself is uncertain. Distances fluctuate, connections shift. The idea of a fixed metric, a fixed way of measuring separation, becomes unreliable. Importantly, this does not mean that space literally tears or breaks in a dramatic sense. It means that the mathematical structures we use to describe smoothness no longer apply cleanly. The failure is conceptual, not catastrophic. The universe does not fall apart. Our descriptions simply stop working the way they used to. One reason this is so difficult to grasp is that smoothness is deeply tied to how the human brain organizes experience. We evolved in a world where continuity was a good approximation. Objects do not teleport. Surfaces do not flicker in and out of existence. Motion is gradual. These assumptions are baked into intuition. Physics has repeatedly shown that intuition is not a reliable guide at extremes. Just as time refuses to behave absolutely at high speeds or strong gravity, space refuses to remain smooth at sufficiently small scales. The refusal is not stubbornness, it is consistency. The universe follows its rules even when those rules undermine our preferred pictures. There is another layer to this problem that comes from how fields behave. In modern physics, particles are understood as excitations of underlying fields that fill space. These fields have values at every point. That description relies heavily on smoothness. A field defined at every point presupposes that points are meaningful and well-defined. At the Planck scale, defining a point becomes problematic. If space fluctuates violently, what does it mean to say that a field has a value at a specific location? The location itself is uncertain. The usual mathematical machinery of fields begins to wobble. This has led some theorists to propose that space is not fundamental at all. Instead, it may emerge from more basic relationships that do not involve geometry in the usual sense. In such views, smooth space is a large-scale approximation. Much like a fluid appears smooth, even though it is made of discrete molecules. In this analogy, The Planck scale is like the scale at which the molecular nature of a fluid becomes impossible to ignore. At that level, talking about smooth flow no longer makes sense. You must switch descriptions. You stop talking about velocity fields and start talking about collisions and interactions. If space behaves similarly, then its refusal to stay smooth is not a flaw. It is a signal that we're using the wrong language. Smooth geometry works well when many underlying elements act together. It fails when we try to isolate the elements themselves. The Planck force again provides a boundary. It marks the regime where gravitational interactions become so intense that geometry cannot be treated as a continuous medium. It hints that there is a stiffness to space-time, a limit to how smoothly it can bend before its underlying structure asserts itself. This perspective changes how we think about emptiness. Empty space, in classical terms, is nothing at all. In quantum terms, it is alive with activity. In a deeper sense, it may be composed of relationships that only look like emptiness when viewed from afar. When smoothness fails, so does the idea of a perfectly quiet vacuum. There is always structure, always motion, always interaction. What changes is our ability to describe it with familiar tools. It is also worth noticing that this breakdown of smoothness does not show up randomly. It appears precisely where different parts of physics demand incompatible things. Quantum mechanics demands uncertainty and fluctuation. General relativity demands that energy shapes geometry. Together, they imply that geometry itself must fluctuate. Smoothness is the casualty. This realization reframes many long-standing puzzles. Singularities, for example, appear in general relativity as points where curvature becomes infinite. These infinities are often taken as signs that the theory has been pushed too far. If space is not smooth at very small scales, then the notion of infinite curvature at a point may be a mathematical artifact rather than a physical reality. In that sense, the refusal of space to stay smooth may be protective. It prevents physical quantities from diverging in unmanageable ways. It forces new descriptions to take over before infinities dominate. As these ideas settle, there is no need to picture them vividly. Visual metaphors tend to fail here. It is enough to recognize the shift. Space transitions from something passive and smooth to something active and structurally limited. It stops being the unquestioned background and starts demanding explanation. This demand is not abrupt. It emerges naturally as we push concepts toward their limits. The Planck scale is not a dramatic cliff. It is a region where familiar assumptions thin out and new questions take their place. From here, attention begins to turn toward the consequences of this roughness. If space is not smooth, how do forces behave within it? How does gravity act when geometry itself is uncertain? What happens when energy is concentrated enough that space cannot respond gently? As the texture of space itself becomes less reliable, attention naturally drifts toward what is causing that restlessness in the first place. Energy has been quietly present in every step of the discussion so far, sometimes obvious, sometimes implied, but always central. In everyday language, energy is something you have or use. You feel energetic or tired. You burn energy to stay warm. Machines consume it to do work. In physics, energy is more subtle. It is not just fuel, it is a bookkeeping tool, a way of tracking how systems change and interact. And when energy meets gravity, the relationship becomes far stranger than our daily experience suggests. Gravity is often introduced as the simplest of forces. Things with mass attract one another. Drop an object, and it falls. The explanation feels intuitive, almost comforting. Even when we learn that gravity is weaker than the other fundamental interactions, it still feels dependable. It shapes planets, stars, and galaxies. It gives weight to bodies and structure to the cosmos. Yet beneath this familiarity lies a detail that becomes crucial as we approach extreme scales. Gravity does not behave like the other forces. Electromagnetism, the strong force, and the weak force all act within space. They push, pull, bind, or transform particles against a background that remains mostly unaffected. Gravity does something different. According to general relativity, gravity is not a force in the usual sense at all. It is the way energy and mass tell space how to curve, and the way that curved space tells matter how to move. This distinction seems subtle at first, but it has deep consequences. When you throw a ball, you can describe its path as being pulled downward by gravity. But from the relativistic perspective, the ball is simply following the straightest possible path through curved space-time. The curvature is not something added on top of space. It is space. This means that gravity is inseparable from geometry. You cannot turn it off or isolate it the way you might shield an electric field. Wherever there is energy, gravity is present, shaping the environment itself. At ordinary scales, this geometric effect is gentle. The curvature caused by everyday objects is so slight that Newton's approximation works beautifully. Space looks flat. Time ticks uniformly. Gravity behaves like a force because the curvature is too small to notice directly. But this calm picture begins to unravel as energy densities increase. Energy density is the key concept here, not just total energy. A mountain contains an enormous amount of mass energy, but it is spread out over a large volume. Its gravitational effect is noticeable, but smooth. Now imagine concentrating that same energy into a much smaller region. The curvature becomes stronger. Space bends more sharply. Time slows relative to distant observers. As this concentration continues, gravity stops being gentle. It becomes intense, dominant, and impossible to ignore. This is the regime where black holes form, where escape becomes impossible, and where classical descriptions begin to strain. The Planck force emerges as a marker of just how extreme this concentration would have to be to push gravity into direct competition with quantum effects at very small scales. Calling the Planck force a force can be misleading. It does not correspond to a particle exchange or a push between objects. Instead, it represents a scale derived from fundamental constants that tells us how stiff space-time is, how resistant it is to deformation. It is a measure of how much energy per unit length space-time can tolerate before its behavior changes qualitatively. At this scale, gravity is no longer the weakest interaction. It becomes comparable in strength to the others, not because gravity itself has changed, but because the context has. When energy is confined to extremely small distances, gravity responds dramatically. The geometry of space becomes tightly coupled to quantum processes. This coupling creates a conceptual problem. Quantum mechanics describes energy as something that fluctuates. Even in the lowest energy state, there is uncertainty. Fields cannot be perfectly still. These fluctuations are usually tiny and inconsequential. But when gravity is sensitive to energy itself, even small fluctuations matter. At the Planck scale, the energy fluctuations predicted by quantum mechanics would produce large fluctuations in curvature. Space would not just bend smoothly, it would jitter, twist, and reconfigure on extremely short timescales. The idea of a stable gravitational field breaks down. This is why the Planck force is better thought of as a boundary condition than an interaction. It tells us that beyond a certain point, treating gravity as a smooth geometric response is no longer viable. The force is not something acting within space. It is a signal that the structure of space itself is under stress. One way to see this is to consider how forces are usually defined. A force causes acceleration. You apply it, and something moves. Gravity, in its geometric form, does not cause acceleration in the same way. Objects in free fall are not being forced, they are following natural paths. What we interpret as gravitational force arises from constraints, like standing on the ground, that prevent us from following those paths. At extreme energy densities, this interpretation becomes even more important. The Planck force does not push objects around. It describes how space-time responds when energy is packed so tightly that geometry can no longer adjust gently. Instead of smooth curvature, you get something closer to a breakdown of the geometric picture itself. This has implications for how we think about limits. There is a maximum speed, the speed of light, that nothing with mass can exceed. There may also be a maximum force, in a certain sense, beyond which space-time refuses to respond in the usual way. The Planck force is often cited in this context. It is not that forces stronger than this cannot exist, but that applying such forces would change the nature of the system so radically that the concept of force becomes inappropriate. Imagine trying to pull on space-time itself. At low intensities it stretches and curves smoothly. At extreme intensities it may form horizons, disconnect regions, or transition into a different state altogether. The Planck force marks the threshold where this transition becomes unavoidable. This perspective also sheds light on why gravity has been so difficult to unify with quantum mechanics. Quantum theories work best when forces act within a fixed background. General relativity insists that the background is dynamic. At everyday energies, this tension can be ignored. At Planck energies, it becomes central. Energy, in quantum mechanics, is something that can be exchanged in discrete amounts. Gravity, in relativity, responds continuously to whatever energy is present. Combining these ideas leads to contradictions unless the underlying picture is revised. The Planck force sits at the crossroads of this revision. It is tempting to imagine that at these scales, gravity turns into something like the other forces, mediated by particles and acting locally. Some theories attempt this, introducing hypothetical particles or new dimensions. Others take a different route, suggesting that quantum mechanics itself must be reformulated to accommodate a dynamic background. Regardless of the approach, the Planck force remains a constraint. Any successful theory must reduce to known physics at lower energies and respect the limits implied by the fundamental constants. It must explain why gravity behaves gently at large scales and violently at small ones, without producing infinities or contradictions. There is also a subtle shift in how causality behaves in this regime. Forces are usually associated with cause and effect. You apply a force, and something happens. But when geometry itself is fluctuating, the ordering of events becomes less clear. Time, which is part of space-time, is affected by the same processes. Near the Planck scale, the distinction between before and after may blur, not in a dramatic, cinematic way, but in a quiet mathematical sense. The equations no longer single out a preferred direction of time. Energy fluctuations and geometric responses become entangled. This does not mean that everyday causality disappears. At larger scales, the averaging over countless microscopic processes restores a clear arrow of time. But at the deepest level, the idea of force as something that acts over time may need reconsideration. In this light, the Planck force is not something you would ever feel or measure directly. It is a concept that helps organize our understanding of where and why familiar ideas stop working. It tells us that gravity's role is not just to move objects, but to define the arena in which movement makes sense. As these ideas settle, it becomes clear that energy is not merely a quantity carried by particles. It is an active ingredient in the structure of reality. Through gravity, it shapes space and time themselves. At modest levels, this shaping is smooth and predictable. At extreme levels, it becomes disruptive. There is a certain elegance in this. The same principles apply everywhere. Energy curves space. Space guides motion. What changes is the intensity. The Planck force marks the point where intensity overwhelms smoothness. If energy and gravity interact so intimately at extreme scales, what happens when quantum rules, which govern energy fluctuations, come into direct conflict with gravitational geometry? How do the rules that describe particles behave when the stage beneath them refuses to stay fixed? At a certain depth, the calm agreement that usually exists between physical rules begins to fray, not loudly, not all at once, but in a way that feels more like tension than conflict. The equations still work, the predictions still hold in isolation. Yet when they are asked to operate together under extreme conditions, they start pulling in different directions. This is the point where quantum rules, which usually cooperate beautifully with experiment, begin to argue with everything else we thought we understood. Quantum mechanics was never meant to feel comfortable. From its earliest days, it challenged intuition. Particles behave like waves. Outcomes are probabilistic rather than certain. Observation plays an active role. Despite this strangeness, quantum theory is extraordinarily successful. It predicts the behavior of atoms, molecules, and particles with precision that borders on the absurd. Modern technology rests on it quietly and reliably. The key to that success is context. Quantum rules were developed to describe systems where gravity is negligible. An electron does not significantly curve space-time. A photon does not distort geometry as it travels. In this regime, space and time can be treated as stable backgrounds. Quantum processes unfold within them without affecting them in return. As long as that separation holds, there is little to argue about. Quantum rules describe what happens inside space-time. Relativity describes how space-time itself behaves. Each theory minds its own domain, and the universe behaves predictably. The disagreement begins when this separation can no longer be maintained. When energy becomes so concentrated that gravity cannot be ignored, quantum processes stop being spectators. They start influencing the stage itself, and the stage in turn starts influencing the processes. Quantum mechanics insists on uncertainty. Energy fluctuates, positions blur, fields cannot sit still. These are not imperfections, they are features. The theory demands them. Relativity, on the other hand, treats energy as a source of curvature. It assumes that energy can be described smoothly, averaged over regions and used to calculate geometry. At ordinary scales, these demands coexist peacefully. Quantum fluctuations are tiny compared to the energies that shape space-time. They average out. Geometry remains smooth. But near the Planck scale, the balance shifts. Fluctuations are no longer small corrections, they are dominant players. This is where the argument begins in earnest. Quantum theory says energy cannot be pinned down precisely. Relativity says geometry depends on energy. If energy is uncertain, then geometry must be uncertain as well. Space and time themselves become subject to quantum rules. The trouble is that quantum mechanics was not built to handle a fluctuating background. Its equations assume a fixed notion of time. They assume distances can be defined. They assume causality has a clear ordering. When space-time becomes uncertain, those assumptions fail. This creates a circular problem. To describe quantum processes, you need space-time. To describe space-time under extreme conditions, you need quantum theory. Each depends on the other, yet neither is formulated to handle that dependence. The Planck force marks the regime where this circularity becomes unavoidable. It signals the scale at which gravitational responses to quantum fluctuations can no longer be ignored. Below this scale, quantum uncertainty directly affects geometry. Above it, geometry smooths things out enough for quantum rules to operate comfortably. When these rules begin to argue, it is not because one is wrong. It is because both are being applied beyond the context they were designed for. The disagreement is a symptom of success, not failure. Each theory works so well in its own domain that extending it reveals exactly where its assumptions lie. Consider how quantum mechanics treats time. Time enters the equations as a parameter, not as an operator. It ticks along steadily, unaffected by what happens within the system. This is acceptable when gravity is weak. Time dilation effects are negligible. Clocks agree. General relativity refuses this simplicity. Time is part of space-time. It slows near massive objects. It stretches and compresses depending on motion and gravity. There is no universal clock. Different observers experience time differently. When quantum rules and relativistic rules are both applied, This difference becomes critical. If time itself is fluctuating, what does it mean for a quantum system to evolve over time? What does it mean to talk about before and after? Quantum theory also relies on locality. Interactions happen at specific points or over small regions. Fields interact locally. Yet if space itself is uncertain, defining locality becomes problematic. What counts as nearby when distances fluctuate? This tension shows up in attempts to calculate quantum corrections to gravity. The mathematics quickly produces infinities. These are not just inconvenient numbers, they are signals that the framework is being pushed beyond its limits. Renormalization techniques that work for other forces fail to tame gravity in the same way. The argument deepens when we consider measurement. Quantum mechanics tells us that measurement affects outcomes. Relativity tells us that measurement depends on space-time geometry. If geometry is fluctuating, measurement becomes deeply entangled with the system being measured in ways that are difficult to separate. This is not an abstract philosophical issue. It has practical consequences for how we define physical quantities. Energy, momentum, and position are all defined relative to space-time. If space-time itself is uncertain, these quantities lose their usual meaning. Some physicists have tried to resolve this by quantizing gravity, treating space-time geometry as another quantum field. In this view, curvature itself fluctuates, existing in superpositions of different geometries. The universe does not have one shape, but many possible ones at once. This approach brings its own challenges. Quantizing gravity leads to a theory that is mathematically complex and difficult to test. It also raises deep questions about interpretation. What does it mean for spacetime to be in a superposition? How does a definite geometry emerge? Others take a different route, suggesting that quantum mechanics must be reformulated to accommodate a dynamic background. Instead of treating time as a parameter, it may need to be treated relationally, defined through correlations between physical systems. In such approaches, time is not fundamental. It emerges from change. A clock is just another physical system, and time is defined by comparing its behavior to others. This idea works well at large scales. At small scales, it becomes essential. The Planck force again serves as a boundary. It marks the scale where these conceptual shifts become unavoidable. Above it, the arguments remain academic. Below it, they shape the structure of any viable theory. It is important to notice that these arguments are not loud or dramatic. They do not manifest as explosions or anomalies in everyday experiments. They exist quietly in the mathematics, waiting for conditions extreme enough to make them relevant. This quietness can be misleading. It can make the disagreement seem remote or speculative, but the same was once true of relativity and quantum mechanics themselves. Their effects were negligible until technology caught up. The Planck scale may remain out of reach for direct experiment, but its conceptual importance is immediate. There is also a human element to this argument. Physicists are trained within frameworks. They learn to trust certain assumptions. When those assumptions conflict, progress slows. New ideas must be developed carefully, without discarding what already works. The disagreement between quantum rules is not a battle for dominance, it is a negotiation. Each side reveals what it needs in order to function. The task is to find a common language where both can coexist. As you sit with this tension, it can help to resist the urge for resolution. There is no final answer waiting just around the corner. The argument itself is informative. It tells us where the seams of our understanding lie. The universe does not care whether our theories agree. It behaves as it does. The fact that our descriptions struggle to keep up is a reflection of our limitations, not a flaw in reality. Imagine trying to hold on to the idea of time as you have always known it, while everything that usually supports it slowly loosens. Not all at once, not dramatically, but in subtle ways that accumulate until the familiar sense of before and after starts to feel less solid. This is the situation we find ourselves in when we move toward the edge where time, as a dependable concept, begins to struggle. It is not that time suddenly stops. It is that the assumptions we rely on to describe it begin to fail quietly one by one. In daily life, time feels straightforward. Seconds follow seconds. Causes precede effects. You remember what happened earlier and anticipate what comes next. Clocks agree with one another well enough that schedules make sense. Even when time feels fast or slow emotionally, there is still an underlying structure everyone shares. A minute is a minute, regardless of how it feels. Physics initially reinforces this comfort. Classical mechanics treats time as a steady parameter, flowing at the same rate everywhere. It does not care what is happening in space or how fast things are moving. Time simply ticks along, impartial and universal. This picture works astonishingly well for most practical purposes, which is why it remained unchallenged for so long. Relativity was the first major crack in that foundation. Einstein showed that time is not universal. It depends on motion and gravity. Clocks moving at different speeds tick at different rates. Clocks closer to massive objects run more slowly than those farther away. Time becomes personal, tied to an observer's path through space-time. Still, even here, time does not break. It stretches, it warps, but it remains part of a smooth geometric structure. Quantum mechanics complicates things in a different way. In quantum theory, time is treated very differently from space. Space-related quantities become operators. They can exist in superpositions. They are subject to uncertainty. Time, by contrast, is kept external. It is a background parameter that orders change. This asymmetry is easy to overlook because it works. Quantum predictions match experiments with extraordinary accuracy. The trouble arises when we try to let these two pictures operate together under extreme conditions. Near the Planck scale, where energy densities become enormous and space-time curvature becomes intense, the comfortable roles assigned to time no longer fit. To see why, it helps to think about what time actually does in our theories. Time orders events. It allows us to say that one thing happened before another. It lets systems evolve. It underpins causality. Remove or destabilize time, and the entire structure of physical explanation starts to wobble. At everyday scales, ordering events is straightforward. Even in relativity, where simultaneity is relative, local cause and effect remain intact. Signals cannot travel faster than light. There is still a clear structure to how influences propagate. Near the Planck scale, this structure becomes uncertain. Quantum fluctuations in energy become large enough to significantly distort spacetime geometry. When geometry fluctuates, the distinction between time and space can blur. Paths that would normally be time-like or space-like can shift unpredictably. The Planck force plays an indirect but crucial role here. It marks the regime where gravitational responses to energy fluctuations are no longer gentle. When spacetime reacts strongly to quantum uncertainty, time itself becomes part of that reaction. It is no longer a stable parameter ordering change. It becomes something that is affected by the very processes it is meant to organize. This leads to a profound problem. Quantum mechanics relies on time to define evolution. A quantum state changes with time according to well-defined equations. But if time itself is uncertain, what does it mean for a state to evolve? This is sometimes called the problem of time, and it is one of the deepest unresolved issues in theoretical physics. It is not a technical nuisance. It strikes at the heart of how we describe reality. In attempts to formulate a quantum theory of gravity, this problem appears almost immediately. Equations that describe the quantum state of the entire universe often contain no explicit time parameter at all. Instead of describing how things change with time, they describe correlations between different configurations. This is deeply counterintuitive. We experience change constantly. Our lives are structured by time. The idea that the most fundamental description of the universe might be timeless feels almost absurd at first. Yet mathematically it arises naturally when the usual role of time breaks down. One way to approach this is to consider time as emergent rather than fundamental. In this view, time is not a basic ingredient of reality. It arises from relationships between systems. When one system changes in a regular way, it can be used as a clock to track change in others. This relational notion of time works well at large scales. We define time by the motion of the Earth, the vibration of atoms, the oscillation of electromagnetic fields. These clocks are reliable because the underlying processes are stable. Near the Planck scale, stability is no longer guaranteed. If spacetime geometry itself fluctuates, then the processes used to define clocks are affected. There is no external reference against which to measure change. Everything participates in the same uncertainty. At this edge, the distinction between past and future can blur. Not in a dramatic sense where events reverse or loop in obvious ways, but in a subtle mathematical sense where the equations no longer privilege one direction over another. The arrow of time, so familiar in thermodynamics and everyday experience, becomes harder to define. Entropy is often invoked to explain the direction of time. Systems tend to move from ordered to disordered states. This provides a statistical arrow that aligns with our experience. But entropy itself depends on counting states, on defining configurations of systems over time. If time loses its usual meaning, entropy becomes a less reliable guide. This does not mean that the arrow of time disappears completely. At larger scales where countless microscopic processes average out, entropy still increases. Time still feels directional. But at the deepest level, that direction may not be fundamental. It may be a large-scale pattern emerging from a more neutral underlying structure. The Planck scale sits at the boundary between these regimes. Above it, time behaves well enough to be treated as a parameter. Below it, that treatment becomes questionable. The Planck force signals the intensity at which spacetime dynamics interfere with the very notion of temporal order. Another way to see the breakdown is through causality. In familiar physics, causes precede effects within light cones. This structure is preserved even in relativity. Near the Planck scale, fluctuating geometry can distort light cones themselves. The distinction between what can influence what becomes fuzzy. Again, this is not something we can observe directly. It is a consequence of extending known theories into regimes where their assumptions collide. The fact that this collision consistently points to trouble with time suggests that time is not as fundamental as it feels. This realization can be unsettling. Time structures memory, identity, and expectation. It is difficult to imagine reality without it. Yet physics has repeatedly shown that deeply ingrained intuitions are not reliable guides at extremes. There is also a quiet elegance in the idea that time emerges rather than exists outright. It suggests that change is primary, and time is a way of organizing that change when conditions allow. When those conditions fail, time fades as a useful concept. The Planck force again functions as a signpost. It does not tell us what replaces time. It tells us where time, as currently understood, can no longer be assumed. Any future theory that hopes to describe this regime must explain how temporal experience emerges from something that is not fundamentally temporal. Some approaches attempt to do this by treating the universe as a collection of events related by correlations rather than sequences. Others focus on entanglement, suggesting that temporal order arises from how quantum systems become correlated with one another. These ideas remain speculative, but they share a common theme. Time is not discarded. It is reinterpreted. It becomes a derived concept, meaningful in certain contexts and absent in others. As you sit with this, it may help to notice how gently the breakdown occurs. There is no sharp line where time stops working. There is a gradual erosion of assumptions. First, simultaneity becomes relative, then clocks disagree, then geometry fluctuates. Eventually, time's role as a universal organizer dissolves. This gradualness mirrors the way scientific understanding often evolves. Concepts are not replaced overnight. They are stretched, qualified, and eventually transformed. Time, it seems, is undergoing that process at the deepest level, The edge of breakdown is not a place of chaos, it is a place of transition. Familiar structures give way to new ones that we do not yet fully understand. The Planck scale marks this transition not because it is magical, but because it is where multiple lines of reasoning converge. For now, it is enough to recognize that time, like space, behaves well only within certain limits. Beyond those limits, it asks to be rethought, not abandoned, but understood in a deeper, more flexible way that can accommodate the full range of physical reality. Not everything dramatic announces itself with noise, but when gravity reaches a certain intensity, subtlety is no longer an option. The effects stop hiding in gentle curves and quiet corrections. They assert themselves openly, reshaping motion, distorting time, and overpowering other influences that usually dominate the small-scale world. This is the regime where gravity, often treated as the weakest interaction, stops whispering and begins to dominate the conversation. Under normal conditions, gravity is easy to overlook. Compared to electromagnetism, it is astonishingly weak. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Chemical bonds, electrical forces, and even thermal motion easily overpower gravity at microscopic scales. This imbalance is why quantum mechanics developed without needing to account for gravity in most situations. The particles it describes simply do not curve space-time enough to matter. That changes when energy becomes dense. Gravity does not care about size in the way other forces do. It cares about energy and momentum, regardless of their form. When energy is spread out, gravity's influence is diluted. When energy is packed tightly into a small region, gravity responds decisively. The phrase, "gravity gets loud," is not meant to suggest sound, but presence. In these regimes, gravity can no longer be treated as a background effect or a small correction. It becomes the defining feature of the system. Everything else must respond to it. The most familiar example of gravity asserting itself is a black hole. When enough mass is compressed into a small enough volume, space-time curves so steeply that not even light can escape. This is not because gravity pulls harder in the usual sense. It is because space-time is shaped in such a way that all paths lead inward. Black holes are often discussed as exotic objects, but from a certain perspective, they are a natural consequence of gravity becoming dominant. They represent the outcome of energy concentration overwhelming the ability of space to respond smoothly. Beyond a certain threshold, collapse becomes unavoidable. As extreme as black holes are, they are still described by classical general relativity. Quantum effects become important near their centers, but the event horizon itself can be understood without invoking quantum mechanics. This is already an indication that gravity's dominance does not immediately imply conceptual breakdown. It does, however, set the stage. The Planck scale represents a further escalation. It marks the point where gravity does not just dominate motion, but interferes directly with quantum processes. At this scale, gravity is no longer merely shaping trajectories. It is shaping the conditions under which those trajectories can even be defined. When gravity gets loud in this sense, space-time becomes highly responsive. Small changes in energy produce large changes in geometry. Quantum fluctuations, which normally average out harmlessly, start leaving visible imprints on the structure of space and time. This leads to a feedback loop. Quantum mechanics predicts fluctuations in energy. Gravity responds by curving space-time. That curvature, in turn, affects how quantum processes unfold. The separation between cause and effect blurs, not because causality disappears, but because the background that supports it is unstable. One way to appreciate this is to think about localization. To say that something happens here and not there requires that here and there be well defined. When gravity is weak, this is not a problem. Distances are stable, coordinates behave. But when gravity responds strongly to energy, defining precise locations becomes difficult. A attempting to localize a quantum particle more precisely requires concentrating energy. That energy increases gravitational effects. Beyond a certain point, trying to localize the particle significantly alters spacetime itself. Instead of learning more about the particle, you end up reshaping the environment. This is where the Planck force becomes relevant again. It signals the scale at which spacetime resists further localization. Gravity does not simply get stronger, it changes the rules of the game. The loudness of gravity in this regime also affects how forces compare. At ordinary scales, gravity is negligible compared to electromagnetism or the strong force. Near the Planck scale, these comparisons break down. Gravity becomes comparable in influence because the energy scales involved are extreme. This does not mean that gravity suddenly acquires a new character. It means that the context has shifted. Gravity's response to energy becomes unavoidable. Other forces continue to operate, but they do so within a space-time that is no longer passive. Another consequence of gravity getting loud is the breakdown of simple time evolution. In classical systems, you can specify initial conditions and evolve them forward in time. Quantum systems complicate this with probabilities, but time still orders change. When gravity dominates and space-time fluctuates, time itself becomes part of the dynamics. In such situations, talking about a system evolving over time may not be the right description. Instead, you may need to talk about correlations between configurations. This shift is subtle, but profound. It changes how explanations are structured. The loudness of gravity also raises questions about limits. Is there a maximum force? Some physicists argue that there is, in a certain sense, and that it is related to the Planck force. Exceeding this limit does not produce arbitrarily large accelerations. Instead, it produces horizons or changes in topology that prevent further increase. This idea fits with what we see in black holes. As mass increases, the event horizon grows. The gravitational pull at the horizon does not become infinite. Instead, the region of influence expands. Gravity asserts itself by restructuring space-time, not by producing unbounded forces. At the Planck scale, similar restructuring may occur at microscopic levels. Instead of infinite forces, space-time may respond by changing its connectivity or dimensionality. These ideas are speculative, but they illustrate a consistent theme. Gravity's loudness expresses itself through geometry, not brute force. There is also an important distinction between loudness and violence. Gravity can be loud without being destructive in the usual sense. It can dominate dynamics while maintaining internal consistency. The universe has been operating under gravitational dominance in certain regions since its earliest moments. In the early universe, energy densities were extremely high. Gravity played a central role in shaping expansion and structure. Quantum processes were also important. The interplay between them left imprints that we can still observe today, such as subtle patterns in cosmic radiation. Those early conditions provide indirect evidence that gravity and quantum mechanics can coexist, at least approximately, even when gravity is loud. The challenge lies in describing that coexistence precisely at the smallest scales. Another place where gravity asserts itself is in the merging of massive objects. When black holes collide, they produce ripples in space-time known as gravitational waves. These waves carry energy and information across vast distances. They're a macroscopic example of gravity becoming audible, in a metaphorical sense. Gravitational waves show that space-time is not rigid. It can vibrate. It can carry energy. This dynamism becomes even more pronounced at smaller scales. Near the Planck scale, space-time may be in a constant state of fluctuation, responding to quantum processes moment by moment. This perspective reframes gravity not as a background influence but as an active participant in every interaction. When gravity is quiet, this participation is subtle. When gravity is loud, it becomes impossible to ignore. The difficulty is that our current theories are optimized for the quiet regime. General relativity handles smooth curvature beautifully. Quantum mechanics handles fixed backgrounds with precision. Neither is comfortable when gravity and quantum effects are equally loud. The Planck force again marks the boundary where this discomfort becomes unavoidable. It does not tell us what happens beyond that boundary in detail. It tells us that the language we're using needs revision. It is tempting to imagine that gravity getting loud would result in chaos, but the universe tends to favour structure. New regimes often come with new organising principles. The challenge is identifying them. Some theories propose that when gravity becomes loud at small scales, spacetime reorganises into discrete units. Others suggest that dimensions behave differently, effectively reducing the number of degrees of freedom. Still others propose entirely new mathematical frameworks. What these ideas share is a recognition that gravity's dominance is transformative. It does not simply amplify existing behaviour, it changes what behaviour is possible. As these possibilities unfold, it becomes clear that gravity's loudness is not an anomaly. It is a natural consequence of pushing energy and scale to their limits. The same rules that make gravity gentle and predictable at large scales make it overwhelming at small ones. There is a certain symmetry in this. Gravity shapes the largest structures in the universe. It may also shape the smallest. In both cases, its influence is geometric, relational, and deeply tied to energy. Pressure is an unassuming concept. You feel it in a tire, in deep water, in a crowded room, but it rarely feels like something that could decide the fate of reality itself. It is simply force spread over area, resistance pushing back against compression, and yet, when particles are packed tightly enough and energy is forced into ever smaller regions, pressure becomes one of the last lines of defense against collapse. Understanding what happens at that boundary requires following pressure down to scales where particles, gravity, and geometry begin to lose their usual roles. In ordinary matter, pressure is what keeps structures intact. The air in a balloon pushes outward, balancing the tension of the rubber. The atoms in a solid resist being squeezed closer together because their electrons repel one another. Even the ground beneath your feet exists in a stable balance between gravitational pull and internal pressure. Without pressure, matter would not hold shape. It would simply fall inward. At the level of particles, this resistance is not mechanical in the everyday sense. It arises from quantum rules. Electrons cannot all occupy the same state. Fermions, a class of particles that includes electrons, protons, and neutrons, obey an exclusion principle that prevents them from piling into identical configurations. This creates what is known as degeneracy pressure, a quantum form of resistance that has nothing to do with temperature or motion in the usual sense. Degeneracy pressure is quiet but powerful. It is what keeps white dwarf stars from collapsing under their own gravity. In these stars, nuclear fuel has run out. There is no longer outward pressure from fusion reactions. Gravity pulls inward relentlessly. What stops the collapse is the quantum pressure of electrons refusing to be compressed beyond a certain point. Push harder, increase the mass, and electrons are no longer enough. In neutron stars, gravity overwhelms electron degeneracy pressure. Electrons combine with protons to form neutrons, and a new form of pressure takes over. Neutron degeneracy pressure, along with strong nuclear interactions, resist further collapse. The star shrinks dramatically, becoming incredibly dense, yet it holds. These astrophysical examples are extreme by everyday standards, but they are still far from the deepest limits. They show that collapse is not immediate. Matter has ways to push back. Pressure, rooted in quantum behaviour, acts as a stabilizing influence even in intense gravitational fields. The question becomes more subtle as we imagine pushing further. What happens when pressure can no longer respond? What happens when gravity overwhelms every known source of resistance? This is where the discussion turns from stars to fundamental limits. At sufficiently high densities, the familiar categories begin to blur. Particles stop behaving like distinct objects. Forces stop acting independently. The geometry of space itself becomes part of the struggle. The Planck scale represents the point where these effects converge. It is not just a matter of gravity pulling harder. It is a matter of space refusing to accommodate further compression without changing its nature. The Planck force marks the regime where attempts to confine energy lead not merely to increased pressure, but to structural changes in space-time. To see why collapse becomes such a difficult question here, it helps to reconsider what collapse means. In everyday terms, collapse is straightforward. Something caves in, a structure fails, matter moves inward. In relativistic terms, collapse means the formation of horizons, regions from which information cannot escape. In quantum terms, collapse has an entirely different meaning associated with measurement and state reduction. Near the Planck scale, all of these meanings intersect uncomfortably. Gravitational collapse suggests the formation of singularities, points where density becomes infinite and curvature diverges. Quantum mechanics resists infinities. It replaces sharp values with probabilities and fluctuations. Pressure, which has served as a reliable counterweight so far, becomes ambiguous. Quantum pressure relies on the structure of space and the definition of states within it. If space itself is fluctuating, what does it mean for particles to occupy states? What does it mean for them to resist compression? This is not a question of missing details. It is a question of compatibility. The mechanisms that generate pressure presuppose a background that remains well defined. At the Planck scale, that presupposition fails. One might imagine that as collapse continues, new forms of pressure appear, just as neutron pressure replaced electron pressure in stars. This is a reasonable instinct grounded in experience. Nature often finds new ways to stabilize systems, but there is a difference here. The known forms of pressure rely on known particles and interactions. At Planck densities, particles themselves may not be meaningful in the usual sense. Energy becomes so concentrated that the distinction between particles and space-time blurs. Attempting to describe pressure as something exerted by particles against confinement may no longer apply. Instead, the resistance may come from space-time itself. This idea appears in several theoretical approaches. Some suggest that space-time has a kind of stiffness, an inherent resistance to curvature beyond a certain point. Others propose that collapse leads not to singularities, but to new phases of geometry, where space reorganizes rather than shrinks indefinitely. In these views, collapse does not end in an infinite point. It transitions into a different state. The Planck force again acts as a threshold. It indicates where ordinary descriptions of pressure and force give way to something more structural. Another way to frame the problem is through energy density. Pressure is related to energy density, but they are not the same. Pressure describes how energy responds to compression. Energy density describes how much energy is present per unit volume. As volume shrinks, energy density rises. Gravity responds to energy density, not pressure alone. At extreme densities, the energy required to further compress a region becomes so great that gravitational effects dominate everything else. The energy added to increase pressure also increases gravity. This creates a feedback loop that accelerates collapse rather than halting it. This is why black hole formation is so difficult to prevent once certain thresholds are crossed. Adding pressure adds energy. Adding energy deepens curvature. Deeper curvature makes escape harder. Pressure becomes part of the collapse rather than a solution to it. At the Planck scale, this loop becomes absolute. Any attempt to resist collapse by adding energy immediately strengthens gravity to the point where resistance fails. The question of collapse becomes inseparable from the structure of spacetime itself. There is also a conceptual issue with defining volume at these scales. Pressure depends on area and volume. If space is not smooth, these concepts become fuzzy. What does it mean to compress something when distance itself fluctuates? What does inward mean when geometry is uncertain? These questions suggest that collapse as we usually imagine it may not be the right description. Instead of matter collapsing into a point, the system may reach a regime where classical notions of inside and outside lose meaning. Some theories propose that what we call collapse is actually a transition to a different geometric configuration. Instead of infinite density, there may be a minimum volume. Instead of a singularity, there may be a region governed by quantum gravitational rules. In such scenarios, pressure does not vanish. It changes character. It is no longer exerted by particles pushing back against confinement. It is embodied in the structure of space-time resisting further deformation. This perspective aligns with the idea of maximum force. The Planck force can be interpreted as the maximum tension space-time can sustain. Beyond this, space-time reorganizes. Collapse does not continue in the same way because the system has entered a new regime. None of this is experimentally confirmed. These ideas exist at the edge of theory, constrained by consistency rather than observation. Yet they are motivated by the same principles that have proven reliable elsewhere. It is also important to notice that collapse is not inherently destructive. From a cosmic perspective, collapse is creative. Stars form from collapsing clouds. Planets form from collapsing disks. Even black holes play a role in shaping galaxies. Collapse redistributes energy and structure. At the deepest level, collapse may be part of how the universe regulates itself. Instead of allowing unbounded densities, it may enforce limits through geometry and quantum behavior. The Planck scale may be where those limits assert themselves. As you consider this, it can help to release the urge for visual clarity. These processes do not resemble familiar crushing or implosion. They involve shifts in description rather than dramatic motion. The drama is conceptual, not cinematic. The question of collapse is ultimately a question about how far compression can go before the rules change. Pressure has served us well as a stabilizing concept. Particles have provided structure. Gravity has shaped large-scale behavior. Near the Planck scale, these elements converge, and their interactions become inseparable. Long before anyone tried to push physics all the way down to the Planck scale, black holes were already quietly warning us that our understanding of reality had limits. They emerged not from speculation, but from the equations of general relativity themselves, appearing as perfectly valid solutions long before anyone believed they could exist. At first, they were treated as mathematical curiosities, strange consequences of equations pushed too far. Over time, observation caught up, and black holes became accepted as real astronomical objects. Yet even now they remain places where physics grows uneasy, where familiar descriptions approach their breaking point, and where the Planck boundary is believed to hover just out of sight. A black hole forms when gravity overwhelms every known form of resistance. Pressure fails. Structural forces collapse. Space-time curves so severely that paths which once led outward now lead inexorably inward. From the outside, the defining feature is the event horizon, a boundary beyond which information cannot escape. Cross that boundary, and no signal, no particle, no light ray can return to tell the story. This horizon is not a physical surface. Nothing solid waits there. An astronaut crossing it would not notice anything special at that exact moment, at least not for large black holes. Locally, physics still feels ordinary. The drama is global, not local. It is written into the structure of space-time itself. Inside the horizon, however, the equations of general relativity predict something far more troubling. They point toward a singularity, a region where curvature becomes infinite, density diverges, and space-time, as described by the theory, simply ceases to make sense. Singularities are not just extreme, they are signs of failure. They indicate that the theory has been pushed beyond the regime where it can provide meaningful answers. This is where the Planck boundary enters the story. While general relativity predicts singularities, many physicists believe that these infinities are not physical realities, but placeholders for unknown physics. The Planck scale is widely suspected to be the domain where those unknown rules take over. To understand why, it helps to consider what a singularity actually represents. In mathematics, an infinity often signals that a model is incomplete. When a function blows up to infinity, it usually means that the assumptions underlying the equation no longer apply. In the case of black holes, The assumption that space-time is smooth and continuous is likely the culprit. As matter collapses inward, densities increase, curvature grows stronger. Eventually, according to classical theory, everything is crushed into an infinitely small point. But before reaching that point, energy densities would surpass the Planck scale. At that moment, quantum effects cannot be ignored. Gravity would be responding to quantum fluctuations. Space itself would be subject to uncertainty. The Planck boundary marks the regime where this transition is expected to occur. It is not a physical wall inside the black hole, it is a conceptual threshold. Beyond it, the language of smooth geometry, trajectories, and continuous collapse loses its reliability. In this sense, the singularity predicted by general relativity may not exist as a point of infinite density. Instead, it may be replaced by a region governed by quantum gravitational effects, where spacetime behaves in ways we do not yet know how to describe. Black holes are especially important in this discussion because they provide a natural laboratory for extreme gravity. Unlike hypothetical Planck-scale experiments, black holes actually exist. They concentrate enormous amounts of energy into relatively small regions. They push space-time toward its limits, yet even black holes keep the Planck boundary hidden. For stellar mass and supermassive black holes, the event horizon forms long before Planck-scale densities are reached. The region where quantum gravity becomes important is buried deep inside, shielded from observation by the horizon. This shielding is both a curse and a clue. It prevents direct observation of Planck-scale physics, but it also suggests that the universe has a way of protecting itself from pathological behaviour. Instead of allowing naked singularities to appear, it wraps extreme regions behind horizons, maintaining consistency for outside observers. Whether this protection is absolute remains an open question. Some solutions to Einstein's equations allow for naked singularities, regions of infinite curvature visible from the outside. Most physicists suspect that some principle, often called cosmic censorship, prevents these from forming in reality. If so, quantum gravity may play a role in enforcing that censorship at the Planck boundary. Another way to approach the issue is through black hole thermodynamics. Black holes are not just gravitational traps. They have temperature, entropy, and energy. They radiate slowly through quantum effects near the horizon, a process known as Hawking radiation. This radiation arises because quantum fields near the horizon behave differently than they do in flat space. Particle-antiparticle pairs form. One falls in, the other escapes. Over immense timescales, the black hole loses mass and can eventually evaporate. Hawking radiation brings quantum mechanics and gravity into direct contact. It shows that black holes are not purely classical objects. Quantum effects matter, even outside the Planck regime. This strengthens the case that quantum gravity must play a role in resolving what happens deep inside. The entropy of a black hole is proportional not to its volume, but to the area of its horizon. This surprising fact suggests that the information content of a region of space may be encoded on its boundary. This idea, known broadly as holography, hints at a radical rethinking of space-time itself. If information is fundamentally associated with surfaces rather than volumes, then the interior of a black hole may not be what classical intuition suggests. The Planck boundary may not enclose a point-like singularity, but a different organizational structure altogether. In holographic frameworks, the Planck scale often appears as the smallest meaningful unit of information. Space emerges from patterns of entanglement rather than existing as a fundamental backdrop. From this perspective, the breakdown of smooth space-time near a singularity is not a catastrophe. It is a transition from one description to another. The Planck force again plays a quiet role here. It represents the scale at which space-time cannot sustain increasing curvature without reorganizing. Instead of infinite compression, geometry responds by changing the rules. Some speculative models replace singularities with bounces, where collapse halts and reverses due to quantum gravitational effects. Others suggest that the interior of a black hole connects to other regions of space-time, or even other universes, through structures that classical theory cannot describe reliably. While these ideas remain untested, they share a common motivation. Singularities are unacceptable endpoints. They signal a breakdown of predictability and physical meaning. The Planck boundary offers a way out, a place where new physics can intervene. It's important to emphasize that none of this implies that black holes are unstable or ill-defined objects. From the outside, they are remarkably simple. They are described by just a few parameters: mass, charge, and spin. This simplicity is part of what makes them so useful as theoretical tools. The complexity is hidden. It lies beyond the horizon, where classical descriptions insist on infinities and quantum reasoning insists on uncertainty. The Planck boundary sits at the intersection of these demands. There is also a deep connection between black holes and the early universe. The Big Bang, when traced backward using classical equations, also leads to a singularity. Just as with black holes, many physicists believe this singularity is not physical, but a sign that new physics takes over at the Planck scale. In both cases, extreme compression leads to the same conceptual failure. Smooth spacetime, continuous time evolution, and well-defined geometry all break down. This parallel strengthens the idea that singularities are placeholders rather than realities. Black holes, then, are not just cosmic curiosities, they are signposts. They show us where our theories work beautifully and where they stop. They guide us toward the Planck boundary not by speculation but by necessity. As observations of black holes improve through gravitational waves and high-resolution imaging, we gain confidence in general relativity's predictions at large scales. This confidence sharpens the mystery at small scales. If the theory works so well almost everywhere, why does it fail so completely at singularities? The most likely answer is not that nature behaves pathologically, but that our description is incomplete. The Planck boundary marks the point where that incompleteness can no longer be ignored. For now, black holes keep their deepest secrets hidden. They do not reveal what replaces the singularity. They only tell us that something must. Something consistent with quantum principles. Something that respects limits on force, curvature, and information. As this understanding settles, the focus naturally begins to shift. If singularities are avoided, if collapse halts or transforms at the Planck boundary, then what is the nature of the structures that replace them? What does spacetime look like when it refuses to be crushed any further? Suppose, for a moment, that you could keep shrinking your view of the universe without ever stopping. Not just zooming in with a better microscope, but genuinely asking whether there is an endpoint to divisibility itself. This question sits quietly beneath much of what we have already explored, and now it comes into focus more directly. Is there a smallest unit of reality, a point beyond which smaller no longer applies, or does the universe allow infinite smoothness all the way down? At first glance, the idea that reality might be pixelated feels strangely modern, shaped by digital screens and compressed images. Zoom in far enough on a photograph, and the smooth curves dissolve into squares. Each pixel is indivisible within that system. You cannot see half a pixel. It is the smallest meaningful unit of that representation. The analogy is tempting, but it also risks misleading us if taken too literally. In physics, the question of whether reality is discrete or continuous has a long history. Ancient philosophers argued about it without mathematics or experiments. Some imagined matter made of indivisible atoms, others believed everything could be divided endlessly. Modern physics inherited this tension and refined it with equations, measurements, and increasingly precise tools. For a long time, continuity won by default. Classical physics treats space and time as smooth. You can always imagine cutting a distance in half, then in half again, without limit. Calculus, which underpins much of physics, depends on this assumption. Motion is defined through infinitesimal changes. Forces act continuously. Geometry behaves politely. Quantum mechanics disrupted this picture, but not in the way people often assume. While energy comes in discrete amounts and certain quantities are quantized, space itself is still treated as continuous in standard quantum theory. A particle's position can take on a continuum of values, even if its energy levels are discrete. The mathematics still relies on smooth space and time. The discomfort returns when gravity enters the picture at extreme scales. As we have seen, attempts to probe smaller distances require higher energies. Those energies gravitate. At some point, the effort to resolve smaller structure produces gravitational effects that undermine the resolution itself. This is where the Planck scale emerges again, not as a measurement result, but as a consistency condition. The idea that reality might be pixelated at the bottom comes from taking this condition seriously. If there is a smallest meaningful length, then space cannot be infinitely divisible in the classical sense. Below that scale, the concept of distance may no longer apply. This does not automatically mean that space is made of little cubes or points arranged on a grid. It means that the language of smooth geometry stops working. One way to approach this is through information. Any measurement extracts information from a system. Information, in physics, is not abstract. It has physical limits. There is a maximum amount of information that can be stored in a given region without forming a black hole. This limits scales with surface area, not volume, which already hints that space behaves differently at fundamental scales. If information is limited, then so is resolution. You cannot pack infinite detail into a finite region. This suggests that there may be a finite number of distinguishable states associated with any given area of space. From this perspective, pixelation is not about little blocks of matter, but about limits on distinguishability. Several approaches to quantum gravity take this idea seriously. They propose that space is composed of discrete elements, not in a rigid lattice, but in networks or relations that only approximate smoothness when viewed collectively. In these models, smooth space emerges the way a fluid surface emerges from molecules. Up close, the smoothness disappears. Loop-based approaches, for example, suggest that areas and volumes come in discrete chunks. You cannot have an arbitrarily small area. There is a smallest unit, determined by the Planck scale. Geometry itself is quantized. Distances are not fundamental, relationships are. Other frameworks focus on causal structure rather than geometry. They treat spacetime as a collection of events ordered by cause and effect, not by coordinates. In these views, spacetime is more like a graph than a surface. Smoothness is an approximation that holds when the graph is large and densely connected. There are also approaches that replace spacetime entirely with algebraic or informational structures. In these, the question of pixelation becomes secondary. Space is not fundamental enough to be pixelated. It emerges from deeper rules governing correlations and interactions. Despite their differences, these ideas converge on a shared intuition. The smooth continuum we experience is likely not fundamental. It is an effective description that works extraordinarily well at large scales and fails gracefully at small ones. It is important to stress that this does not mean reality becomes simple at the bottom. Discreteness does not imply ease of understanding. A discrete system can be vastly complex. The rules governing it may be unfamiliar, counterintuitive, and difficult to express in ordinary language. There is also a subtle distinction between discreteness and granularity. Granular materials like sand are made of discrete pieces, but the pieces themselves occupy space in a continuous way. Fundamental discreteness would be different. It would mean that certain questions simply cannot be asked. You cannot ask what lies between two adjacent units if between has no meaning. This brings us back to measurement. If space is pixelated, then measuring distances smaller than a fundamental unit is meaningless, not merely impractical. The universe does not hide that information. It does not exist within the framework being used. This idea challenges deeply held assumptions. Science is often portrayed as uncovering ever finer detail. Pixelation suggests that detail eventually runs out, not because of ignorance, but because of structure. Yet this limit can also be seen as protective. Without it, theories produce infinities. Quantities diverge. Predictions lose meaning. A fundamental cutoff may be what keeps the universe mathematically and physically consistent. The Planck force fits naturally into this picture. It represents the scale at which attempts to impose finer structure fail. Gravity responds not by allowing further compression, but by reorganizing spacetime. Pixelation, if it exists, is enforced not by fiat but by dynamics. Another way to think about this is through waves. In quantum mechanics, particles are associated with wavelengths. Shorter wavelengths correspond to higher energies. To probe smaller structures, you need shorter wavelengths. At some point, the required wavelength corresponds to energies that significantly curve spacetime. The wave collapses into geometry. Resolution turns into gravity. This suggests that pixelation is not imposed externally. It emerges from the interplay of quantum mechanics and gravity. The universe resists being examined below a certain scale because examination itself becomes destructive. There is also an important conceptual point about symmetry. Many physical laws rely on continuous symmetries. Translational symmetry assumes that space is the same everywhere and divisible without limit. If space is fundamentally discrete, these symmetries cannot be exact. They must be approximate. This raises concerns. Continuous symmetries underpin conservation laws. Energy conservation, momentum conservation, and other foundational principles are tied to smoothness. If smoothness fails, do these principles fail as well? The answer appears to be no, at least not at scales we can access. Just as the discrete structure of matter does not prevent fluids from obeying smooth equations at large scales, a discrete spacetime could still support approximate symmetries. Conservation laws would emerge rather than vanish. This is a familiar pattern in physics. Exact rules at one level become approximate at another. What matters is not whether the underlying structure is discrete or continuous, but whether the effective description remains stable. The question of pixelation also intersects with time. If space is discrete, is time discrete as well? Is there a smallest moment? Some theories suggest so. Others treat time differently, allowing it to remain continuous even if space is not. This asymmetry reflects our incomplete understanding. Time has always been harder to pin down than space. Whether it is pixelated, emergent, or something else entirely remains open. There is also a psychological dimension to this question. Humans are comfortable with objects and surfaces. We are less comfortable with networks, relations, and abstract structures. Pixelation sounds comforting because it resembles familiar digital metaphors. But the underlying reality, if discrete, may not resemble pixels at all. It may be more accurate to think in terms of limits on description rather than building blocks. The universe may not be made of pieces. It may be constrained by rules that limit how finely it can be described. In this view, asking whether reality is pixelated is like asking whether temperature is made of degrees. Degrees are a way of describing thermal behavior, not constituents of it. Similarly, Planck scale discreteness may reflect limits of description rather than literal tiles of existence. Still, the fact that multiple independent lines of reasoning point toward a fundamental scale is hard to ignore. The convergence of quantum uncertainty, gravitational collapse, information bounds, and theoretical consistency all suggest that something changes at the bottom. That change does not announce itself with a new particle or a new force. It announces itself through silence, through the failure of familiar questions. How much smaller? Stops being meaningful. Where exactly? Loses precision. When exactly? Becomes ambiguous. From a certain perspective, this is not disappointing. It is elegant. The universe allows complexity, structure, and variation, but within bounds that prevent contradiction. It supports richness without allowing breakdown. It naturally leads to another question. If smooth space is an approximation, and if discreteness or relational structure lies beneath, how do our current theories attempt to bridge that gap? What frameworks try to explain how the smooth world we experience emerges from something fundamentally different? Rather than arriving all at once as a single grand idea, the attempts to hold everything together have emerged slowly, built from necessity rather than ambition. Each one begins at the same uncomfortable realization. The theories that describe the universe so well in isolation stop agreeing with one another when pushed to their limits. Quantum mechanics explains the small, general relativity explains the large. When gravity, energy, space, time, and quantum rules are all forced into the same corner, something has to give. What follows is not one theory, but a landscape of approaches, each trying in its own way to restore consistency without breaking what already works. The motivation behind these efforts is not aesthetic, it is structural. Our current theories make incompatible demands. Quantum mechanics requires uncertainty, discreteness, and probabilistic evolution against a stable background. General relativity requires a dynamic background shaped by energy and momentum. When energy fluctuates quantum mechanically, space-time itself must fluctuate. Yet the mathematical language of quantum theory assumes space-time is fixed. This contradiction cannot be ignored once energies approach the Planck scale. Any theory that tries to hold everything together must satisfy several constraints at once. It must reduce to quantum mechanics where gravity is negligible. It must reduce to general relativity where quantum effects average out. It must avoid infinities. It must respect limits on information, force, and measurement. And it must do all of this without contradicting the vast body of experimental evidence that already exists. One of the earliest and most persistent approaches is the idea of quantizing gravity directly. If the other forces are described by quantum fields, perhaps gravity should be too. In this view, space-time geometry itself becomes subject to quantum uncertainty. Curvature fluctuates. Distances exist in superposition. The gravitational field is treated like any other field, with quanta that mediate interactions. This approach sounds straightforward, but it runs into immediate difficulty. When gravity is treated as a quantum field using standard techniques, the resulting theory produces uncontrollable infinities. The usual methods that tame these divergences for other forces fail. The problem is not technical inconvenience. It is a sign that the underlying assumptions are incompatible. Some physicists interpret this as a hint that gravity is not just another force. It is tied too deeply to the structure of space-time to be quantized in the same way. This realization has pushed research in several different directions. One influential direction reimagines space-time itself as a quantum object from the start. Instead of assuming a smooth background and adding quantum fluctuations, these approaches begin with discrete or relational structures. Geometry emerges rather than being imposed. In loop-based approaches, space is described in terms of networks. These networks are not embedded in space, they define space. Nodes and links carry information about areas and volumes. Smooth geometry arises only when many of these elements are considered together. At small scales, space is granular, but not in a simple grid-like way. It is combinatorial and relational. In such frameworks, the Planck scale appears naturally as the scale of the smallest non-zero geometric quantities. Areas and volumes cannot shrink indefinitely. There is a built-in cutoff that prevents singularities. Collapse halts not because of a force pushing back, but because geometry itself has a minimum structure. Time in these approaches is often treated differently from space. Instead of being a fundamental parameter, it emerges from change. Evolution is described relationally, by comparing configurations rather than by tracking motion through an external clock. This aligns naturally with the breakdown of time we encounter near the Planck scale. Another broad family of ideas takes a more radical step. Rather than modifying geometry directly, it replaces space-time with more abstract mathematical structures. In these views, space-time is not fundamental at all. It is an emergent phenomenon arising from deeper principles. One such principle is symmetry. Some theories suggest that space-time emerges from algebraic relationships between quantum states. Geometry is not assumed, it is derived. Distances correspond to correlations. Proximity reflects interaction strength rather than physical separation. Closely related are approaches centered on information. These treat the universe as fundamentally informational, with physical laws emerging from constraints on how information can be stored, processed, and transmitted. The limits imposed by black hole entropy, the Planck scale, and the speed of light are not afterthoughts. They are foundational. In these frameworks, the Planck boundary is not where physics stops. It is where information density reaches its maximum. Beyond this point, adding more information does not reveal finer detail. It changes the system qualitatively, often by forming horizons or reorganizing degrees of freedom. Holographic ideas sit at the intersection of geometry and information. They suggest that the information contained within a region of space can be described entirely by degrees of freedom living on its boundary. Volume emerges from surface data. This idea is supported by black hole thermodynamics and has been realized mathematically in certain highly symmetric models. If holography is a general feature of reality, then the smooth interior of space-time is not fundamental. It is a derived construct. The Planck scale then represents the resolution limit of this encoding. Pixelation, if it exists, is informational rather than geometric. There are also approaches that extend space-time itself by adding dimensions. In these theories, the familiar 4 dimensions are part of a larger structure. Gravity appears weak in our observed dimensions because it spreads into additional ones. At small scales, these extra dimensions become relevant, altering gravitational behavior. In such models, the Planck scale may not be fundamental in the same way. It could be an effective scale resulting from hidden structure. However, these theories still face the challenge of explaining why space-time behaves smoothly at large scales and why quantum effects remain controlled. Another line of thought abandons the idea of unification altogether, at least in the traditional sense. Instead of forcing quantum mechanics and gravity into a single framework, it seeks consistent ways for them to coexist without contradiction. This involves carefully defining the domains where each applies and understanding how they transition. In these views, the Planck scale is not a place where new particles or forces appear, but where descriptions overlap and must be matched carefully. The emphasis shifts from finding a single equation to understanding how different approximations relate. Despite their diversity, all of these theories share common themes. They treat the Planck scale as a boundary of description rather than a physical object. They replace smoothness with discreteness or relations. They reinterpret time as emergent or relational. They limit information density and force. What differs is the starting point. Some begin with geometry and modify it. Others begin with quantum theory and expand it. Others begin with information and derive both. None of these approaches has yet been confirmed experimentally. All remain provisional. This uncertainty is not a weakness. It reflects the difficulty of the problem. Nature does not offer easy clues at these scales. The Planck boundary is well beyond direct experimental reach. Progress relies on consistency, mathematical coherence, and indirect connections to known physics. It is also worth noting that many of these theories are not mutually exclusive. They may be different descriptions of the same underlying structure, much as wave and particle descriptions coexist in quantum mechanics. The final picture may incorporate elements from several approaches. There is a temptation to ask which theory is correct. That question may be premature. Historically, major advances often come not from choosing between existing ideas, but from reframing the problem entirely. The tension between quantum mechanics and gravity may require a conceptual shift as profound as those that produced either theory in the first place. As these efforts continue, they influence how physicists think about everything from black holes to cosmology. Questions about the origin of the universe, the nature of space-time, and the limits of measurement all feed back into the search for consistency. Theories that try to hold it all together are not just attempts at technical unification, they are attempts to preserve meaning. They aim to ensure that concepts like cause, structure, and predictability survive even at the deepest levels. For now, no single framework has emerged as definitive. Each illuminates part of the problem while leaving others in shadow. Together they sketch the outline of a reality where space, time, and matter are not fundamental ingredients, but emergent features shaped by deeper rules. From this vantage point, the Planck scale stops looking like an obstacle and starts looking like a guide. It tells us where to stop trusting familiar pictures and where to begin imagining new ones. And as attention naturally turns from theory to limitation, from possibility to restraint, the next question arises almost on its own. If these theories are constrained so tightly by consistency, what prevents us from looking any deeper? And why has the universe made that boundary so difficult to cross? Reaching the point where physics has to admit it cannot yet look any deeper is not a moment of failure, but one of clarity. It arrives not with drama, but with careful accounting. After centuries of refinement, after equations that predict reality to astonishing precision, the limits now come not from a lack of imagination, but from the structure of the universe itself and the tools we use to question it. Physics advances by asking questions that can be tested. That requirement sounds simple, but it hides an enormous amount of complexity. To look deeper, you need access. Access requires energy, resolution, and control. Each step inward, each attempt to probe smaller scales, demands more concentrated energy and finer discrimination. Eventually, those demands collide with the same boundaries we have been circling around all along. At everyday scales, looking deeper is straightforward. You build a better microscope, increase magnification, improve sensors. At atomic scales, you accelerate particles and smash them together, inferring structure from the debris. This strategy has worked remarkably well. It revealed nuclei, quarks, and a zoo of particles that form the foundation of modern physics. What makes the current boundary different is that the act of looking deeper changes the subject in a fundamental way. This is not a matter of disturbance, like a measurement slightly altering a system. It is a matter of transformation. To access smaller scales, you must concentrate energy. Concentrated energy gravitates. Gravity reshapes space-time. Eventually, the act of probing creates the very phenomena that block further probing. This is the core reason physics cannot yet look any deeper. The limitation is not primarily technological. Even with perfect engineering, infinite funding, and ideal materials, the underlying constraints would remain. The universe responds to interrogation in ways that prevent unlimited scrutiny. Consider what it would take to directly probe the Planck scale. You would need to localize energy within a region on the order of the Planck length. That localization requires extraordinarily high energies, far beyond anything achievable with current or foreseeable accelerators. But even imagining such energies is not enough. Packing that much energy into such a small region would trigger intense gravitational effects. Instead of revealing finer detail, the region would collapse or form a horizon. Information would be hidden rather than exposed. The universe would not reveal smaller structure. It would reorganize itself to prevent access. This is not a technical obstacle that can be engineered away. It is a conceptual one. The rules that allow measurement at larger scales actively prevent it at smaller ones. Physics, as an experimental science, relies on the ability to isolate systems and extract information. Near the Planck boundary, isolation becomes impossible. There is also the problem of scale separation. Much of physics works because different scales decouple. You can study atomic behavior without worrying about galaxies. You can study planetary motion without worrying about quarks. This separation allows effective theories to operate independently. At the Planck scale, that separation disappears. Quantum effects, gravitational effects, space-time structure, and information limits all converge. There is no clean way to isolate one aspect without invoking the others. Any attempt to look deeper drags the entire framework with it. Another limitation comes from time. Probing small distances requires not only high energy, but extremely short timescales. The Planck time represents the shortest meaningful interval associated with the Planck length. To observe processes at that scale, you would need temporal resolution beyond what spacetime itself may support. If time is emergent or fluctuating at those scales, then defining a sequence of events becomes problematic. Observation requires ordering. Without stable time, observation loses its footing. There is also a limitation rooted in statistics. Many of the phenomena we study rely on repeated measurements. You perform an experiment many times, gather data, and extract patterns. At the Planck scale, repeating experiments becomes meaningless. Each attempt would involve energies so extreme that the system would not return to a comparable initial state. This means that even in principle, the usual statistical tools of science may not apply. You cannot average over many trials if each trial fundamentally alters the conditions. Theoretical physics tries to compensate for this lack of direct access through consistency arguments. If a proposed theory behaves correctly at known scales, avoids contradictions, respects limits on information and force, and recovers existing theories where appropriate, it is considered viable. This is powerful, but it is not the same as experimental confirmation. As a result, multiple theories can coexist, each consistent in its own way, yet incompatible with one another. Without experimental data to discriminate between them, physics cannot decide which description, if any, is correct. This situation is unusual, but not unprecedented. Before quantum mechanics, classical physics faced similar ambiguities. Multiple models explained known data, but only experiments at new scales resolved the conflict. The difference now is that new scales may be fundamentally inaccessible. This does not mean progress has stopped. It means progress has shifted. Instead of drilling deeper through experiment, physics is refining its understanding of limits, constraints, and emergence. The focus has moved from what lies beneath to how what we see arises. One reason this boundary is so difficult to cross is that our instruments are made of the same stuff we are trying to probe. You cannot build a detector immune to quantum uncertainty or gravity. Any apparatus obeys the same rules as the system under study. At small scales, this mutual obedience becomes restrictive. Even thought experiments reveal the same conclusion. Imagine probes, idealized observers, and perfect clocks all encounter the same issues. The limitations are not artifacts of imperfect imagination. They are built into the structure of the theories themselves. There is also a deeper philosophical issue. Physics relies on operational definitions. Length is what you measure with a ruler. Time is what you measure with a clock. Energy is what you infer from motion and interaction. If rulers and clocks lose meaning at certain scales, then the quantities they define lose meaning as well. This does not mean reality stops. It means description stops. The universe does not owe us a vocabulary that works at all scales. It only behaves consistently. Another way to see this is through symmetry. Many physical laws rely on continuous symmetries that assume smooth spacetime. If spacetime has a fundamental limit, these symmetries become approximate. Physics has tools for dealing with approximate symmetries, but those tools depend on knowing the corrections. Without access to deeper scales, those corrections remain speculative. Physics cannot yet determine whether spacetime is discrete, relational, emergent, or something else entirely. It can only constrain possibilities. There is also the issue of energy availability in the universe itself. Even if technology could in principle reach Planck energies, the total energy required would be enormous. Concentrating it locally without triggering gravitational collapse may be impossible even in principle. In this sense, the universe is not just hiding its deepest layer. It is structured in a way that prevents direct access. The Planck boundary functions like a horizon, not necessarily in space, but in inquiry. Some physicists suspect that indirect access may still be possible. subtle imprints of Planck scale physics might appear in cosmological data, such as patterns in the early universe or deviations from expected behaviour in extreme environments. These hints are difficult to interpret and often ambiguous, but they offer a potential path forward. Others believe that the deepest layer may never be observable, even indirectly. In this view, physics reaches a natural stopping point, not because questions end, but because answers become underdetermined. This possibility is uncomfortable for a discipline built on discovery, yet it is not unprecedented. Mathematics, too, encounters undecidable propositions. Limits do not invalidate the enterprise, they define its scope. There is also an important distinction between cannot look deeper yet and cannot look deeper ever. The word yet matters. New ideas can change what we consider accessible. Concepts that seem impossible to probe today may become approachable through unexpected connections. However, even optimism must respect consistency. Any new method must still obey the same fundamental constraints. It cannot violate causality, information limits, or the response of space-time to energy. In that sense, the Planck boundary is not a technological challenge waiting to be solved. It is a structural feature of reality that any solution must accommodate rather than overcome. This realization shifts the role of theory. Instead of predicting new particles to be discovered by larger machines, theories at this frontier aim to explain why discovery itself becomes constrained. They seek to explain the silence as much as the signal. That silence is not empty, it is structured. It arises from the convergence of quantum uncertainty, gravitational response, and informational limits. Each of these principles has been tested extensively in accessible regimes. Their combined implications at extreme scales are not arbitrary. Physics cannot yet look any deeper, because looking deeper would require breaking the very rules that make physics possible. Measurement, repetition, isolation, and ordering all depend on conditions that fail near the Planck scale. This is not an ending, it is a pause, a recognition that some questions may need to be reframed rather than answered directly. If the deepest layer is inaccessible, then the structure of the layers we can access becomes even more important. How does the smooth world we experience arise from a domain we cannot directly probe? Beneath all the limits we have traced, beneath the places where equations fall silent and measurement loses its grip, there is an unavoidable curiosity that remains. If physics cannot look any deeper yet, it is natural to wonder whether there is something there to be seen at all, or whether the idea of there has quietly stopped applying. The universe may not be hiding secrets in the way a locked drawer hides objects, but it may be withholding entire modes of description, structures that only make sense when the questions themselves change. When people imagine hidden layers of reality, the instinct is often to picture smaller things, smaller particles, finer building blocks, a deeper stack beneath the known ones. This way of thinking has served physics well for a long time. Atoms gave way to nuclei. Nuclei revealed protons and neutrons. Those in turn resolved into quarks. Each step inward uncovered new structure. What makes the current boundary different is that the pattern itself appears to be breaking. The Planck scale does not suggest a new particle waiting to be discovered with enough energy. It suggests that the very act of looking for smaller constituents may no longer be the right approach. The universe may not be hiding smaller objects. It may be hiding a different kind of organization altogether. One possibility is that what lies beneath space and time is not substance, but relation. Instead of objects located in space, there may be networks of relationships that give rise to space when viewed collectively. In this view, distance is not fundamental. It emerges from patterns of interaction. Nearness is defined by connection, not by metric separation. If this is the case, then asking what is down there in spatial terms is already a misstep. There is no down, no beneath, no smaller region to point to. There is only a different level of description, one that does not map neatly onto spatial intuition. Another possibility centers on information. Modern physics has steadily elevated information from a bookkeeping tool to a central concept. Entropy, once a measure of disorder, is now understood as a measure of missing information. Black holes, once thought to destroy information, now appear to encode it on their boundaries. From this perspective, the universe may be hiding not matter, but rules about information itself. There may be fundamental constraints on how information is created, stored and transformed. Space and time could be secondary effects, arising from how information flows. If information is primary, then the Planck scale may represent the smallest meaningful unit of informational distinction. Below that, questions about location, duration, and structure dissolve into questions about correlation and encoding. The universe would not be hiding details, it would be enforcing coherence. There is also the possibility that what is hidden is not static structure but process. Physics often describes the world in terms of states evolving over time, but at the deepest level the universe may be fundamentally processual, with no fixed states at all. What exists is change, not things. In such a framework, asking what exists at the bottom is like asking what lies beneath a verb. The question assumes a noun-based ontology that may not apply. The Planck boundary then marks the point where state-based descriptions give way to something more fluid. This idea resonates with the breakdown of time we encountered earlier. If time is emergent, then the deepest layer of reality may not be ordered temporally. It may not make sense to talk about before and after. What exists could be a timeless structure from which temporal sequences emerge only in certain regimes. The universe, in this sense, would not be hiding a place or an object. It would be hiding a mode of existence that does not align with human intuition. That mode would only reveal itself indirectly, through the way higher-level structures behave. There is also the possibility that what is hidden is simplicity. At first glance, this sounds backward. We expect deeper layers to be more complex. Yet physics has a history of revealing simpler principles beneath apparent complexity. Symmetry, conservation laws, and minimal principles often underlie rich phenomena. The Planck scale might be the point where the universe simplifies dramatically. Not in a way we can visualize, but in a way that reduces the number of independent ingredients. Space, time, matter, and force could all be manifestations of a single underlying principle, expressed differently depending on context. If so, then the reason physics cannot yet look deeper is not because the layer is complicated, but because it is too simple for our current categories. Our theories are built to handle distinctions. A layer where distinctions blur or vanish would resist articulation. Another possibility involves dimensionality. The universe we experience has 3 dimensions of space and 1 of time. This arrangement feels fundamental, but there is no deep reason it must be so. Some theories suggest that dimensionality itself emerges. At very small scales, the effective number of dimensions may change. In some models, spacetime behaves as though it has fewer dimensions at high energies. This reduction can tame infinities and make quantum gravity more manageable. If this is correct, then what the universe is hiding is not new content, but a different geometric regime. At large scales, space spreads out in 3 dimensions. At small scales, it may collapse into something effectively lower dimensional. This would radically alter how forces behave and how interactions unfold. Yet from our vantage point, the transition would be invisible, masked by the Planck boundary. There is also the unsettling possibility that what is hidden is indeterminacy itself. Quantum mechanics already challenges the idea that every question has a definite answer. At deeper levels, this may intensify. Some questions may not merely be unanswered, but unanswerable in principle. This is not ignorance, it is structure. The universe may not contain facts corresponding to certain questions. Asking them may be like asking what colour a sound is. The Planck scale may mark the boundary where meaningful questions give way to category errors. In this light, the universe is not hiding information maliciously. It is simply not obligated to conform to human expectations about explanation. Physics, as a human enterprise seeks answers that can be framed, tested, and communicated. The deepest layer may not cooperate with that project. There is also a quieter possibility, one that is often overlooked. The universe may not be hiding anything dramatic at all. The Planck boundary may simply mark the limit of resolution, beyond which there is no additional structure to reveal. Reality may be finite in its descriptive depth. This idea is difficult to accept because it clashes with the intuition that there is always more. Yet finiteness does not imply triviality. A finite structure can support infinite variety at higher levels. Language is finite, music is finite, yet both allow endless expression. If spacetime and physics are grounded in a finite set of principles or states, that finiteness may be what makes the universe stable and intelligible. Infinite regress is not always a virtue. Whatever the truth, it is clear that what lies beyond the Planck boundary cannot be approached by force. Larger accelerators, higher energies, and finer probes do not help. They trigger the same protective responses. Gravity curves, horizons form, information hides itself. This suggests that access, if it exists at all, must come through understanding rather than intrusion. The universe may be hiding its deepest layer not behind a barrier, but behind a change in perspective. The right questions may not be smaller, but different. This is a familiar pattern in science. Before relativity, people asked how objects move through space and time. Relativity reframed the question, revealing that space and time are part of what moves. Before quantum mechanics, people asked what particles are doing when not observed. Quantum theory reframed the question, focusing on probabilities and outcomes. The Planck boundary may be calling for a similar reframing. Instead of asking what is there, we may need to ask how what we experience comes to be. Instead of looking for constituents, we may need to look for principles of emergence. The universe may be hiding rules about how complexity arises from simplicity, how continuity arises from discreteness, how time arises from change, and how space arises from relation. These rules would not live at a location. They would govern transitions. This would explain why the boundary is so hard to cross. You cannot travel to a rule. You can only infer it from behavior. The deepest layer may not be something you can visit, even in principle. It may only be something you can recognize. As you sit with this possibility, it can be helpful to let go of the idea that hiding implies intention. The universe is not concealing secrets in a deliberate way. It is structured such that certain descriptions apply only within certain regimes. Beyond those regimes, new descriptions are required. The Planck scale marks one such transition. It is where familiar descriptions of force, space, time, and objecthood lose their authority. What replaces them may be subtle, relational, informational, or even ineffable in ordinary language. This does not diminish the value of what we already know. On the contrary, it highlights how extraordinary it is that the universe allows so much structure to be understood at all. The fact that laws hold, that patterns repeat, that predictions work across vast scales is remarkable. What the universe might be hiding down there is not chaos, but coherence of a different kind. A coherence that does not announce itself through smaller pieces, but through limits, consistencies, and emergent order. Gradually, without any sharp turn or clear dividing line, attention begins to move away from the deepest limits and back towards scales that feel more familiar. Not because the smallest questions have been answered, but because they no longer need to be held so tightly. There is a natural easing that happens after spending time near the edges of understanding, a gentle return that does not abandon curiosity, but allows it to rest. After tracing ideas down to where size loses meaning, where force becomes a boundary rather than an interaction, and where time itself hesitates, it can feel grounding to notice how effortlessly the mind shifts when given permission. You do not have to solve what lies beneath the Planck scale to feel its effect. The mere fact that such limits exist changes how everything above them is seen. The universe, at human scales, is remarkably cooperative. Space feels smooth. Time flows in a steady enough way to build memories and expectations. Objects persist. Causes tend to precede effects. These are not trivial achievements. They are the result of countless deeper processes averaging out, stabilizing and aligning just enough to create a world that can be navigated without constant confusion. Thinking back to the smallest scales we explored, it becomes clear that the smoothness we experience is not guaranteed. It is earned. It emerges from layers of structure that remain hidden not because they are forbidden, but because they are not needed for everyday existence. The universe does not require us to understand its deepest rules in order to participate in it. This is a comforting thought. You do not need to picture quantum foam, Planck forces, or fluctuating geometry to take a breath, to feel the weight of your body supported, or to notice the quiet rhythm of your surroundings. Those experiences are valid and complete at their own level. In physics, there is a concept called effective description. It means that a theory does not need to be fundamental to be useful or true within its domain. Fluid dynamics works without tracking individual molecules. Thermodynamics works without knowing the exact positions of atoms. These descriptions are not approximations in a dismissive sense. They are accurate where they apply. The same idea extends naturally to experience. You do not need the deepest description of reality to exist comfortably within it. The universe offers layers of explanation, and it does not demand that all of them be engaged at once. As the focus drifts outward from the Planck boundary, the extremes soften, energy densities drop, gravity quiets, quantum fluctuations average out, space becomes reliable again, time regains its familiar ordering. The arguments between theories fade into the background, not because they are resolved, but because their consequences become negligible. This fading is not a loss, it is a feature. It allows complex structures to form, it allows stars to burn steadily, planets to orbit predictably, and life to persist long enough to wonder about its origins. Even the inability to look deeper has a kind of generosity to it. If every layer of reality were equally accessible, the world might be overwhelming. Limits create stability. Boundaries allow patterns to persist. From this perspective, the Planck scale is not an abyss. It is a foundation that does not demand attention. It holds everything else quietly, without asking to be seen. There is a parallel here with human awareness. Most of the processes that keep you alive operate without conscious involvement. You do not think about each heartbeat or each chemical reaction. They happen reliably in the background. Awareness is reserved for what needs attention. The deepest layers of physics may function in the same way. They support reality without intruding into experience. They set limits, enforce consistency, and then recede. As the mind relaxes its grip on the smallest scales, it becomes easier to notice the present moment again. The room you are in, the subtle sounds, or perhaps the absence of them, the steady pull of gravity, gentle and constant. These are expressions of the same laws we've been discussing, but in their quietest, most cooperative form. Gravity here is not loud. It does not curve space dramatically or threaten collapse. It simply provides orientation. It tells you which way is down, and in doing so, it makes rest possible. Time here does not hesitate or blur. It moves forward at a pace slow enough to follow, predictable enough to trust. You do not have to question whether moments are ordered correctly. They simply arrive. Space here does not fluctuate. Distances are stable. Objects remain where they are expected to be. The smoothness that fails at extreme scales is more than sufficient here. This contrast is worth lingering on. The same universe that refuses to be examined beyond a certain depth is also the one that allows calm, continuity, and repetition at everyday scales. There is no contradiction in this. The refusal and the generosity come from the same structure. It can be tempting to think that mystery demands tension, that unanswered questions should feel sharp or urgent. But the mysteries at the foundation of reality do not behave that way. They are patient. They do not rush. They remain whether or not we attend to them. That patience can be mirrored. You do not need to carry every unresolved question with you into rest. Curiosity does not vanish when it is set down. It waits. The human tendency to seek closure often clashes with the nature of fundamental inquiry. Some questions do not close. They remain open, not as wounds, but as spaces. Spaces where understanding can deepen slowly, over generations, or perhaps remain asymptotic, always approached but never reached. There is no failure in that. Many of the most meaningful structures in life are not resolved. They are lived with. As the journey away from the smallest scales continues, it becomes apparent that nothing essential has been lost by stepping back. The universe at accessible scales is not a lesser version of itself. It is the version designed to be inhabited. Theories that try to unify everything are valuable, but they are not required for peace of mind. They are part of a long collective effort to understand, not a prerequisite for existing. The fact that physics cannot yet look deeper does not diminish what it can see. It can still describe the motion of galaxies, the structure of atoms, the behavior of light, and the patterns of energy with extraordinary accuracy. That achievement stands on its own. There is also a quiet humility in recognizing limits. It reminds us that knowledge is contextual. It grows, adapts, and sometimes pauses. Pausing is not stagnation. It is often preparation. As you allow the ideas from this exploration to settle, they do not need to be organized or retained precisely. They can blur at the edges. They can overlap. They can fade. Understanding does not require constant clarity. The universe itself tolerates ambiguity at its deepest level. It allows uncertainty, fluctuation, and indeterminacy without falling apart. There is something reassuring in that parallel. Rest does not require resolution. Sleep does not demand answers. The mind does not need to hold the Planck scale in focus to let go. In a way, drifting back from the smaller scale mirrors the process of falling asleep. Attention narrows, then softens. Sharp distinctions dissolve. The urge to analyze relaxes. Thoughts continue, but they lose urgency. The structures that govern the universe do not stop when attention drifts. Gravity continues to curve space gently. Time continues to pass. Space remains stable. There is nothing you need to manage. If anything, the deepest lesson of exploring the Planck boundary may be that control is not required. The universe holds itself together without supervision. The same consistency that enforces limits also sustains calm. As this realization settles, there is room to let curiosity transform into quiet appreciation. Not for answers, but for structure. Not for certainty, but for coherence. The smallest scale remains where it is, unreachable for now, doing its work silently. The larger scales remain accessible, navigable, and forgiving. Between these layers there is space for rest, and without closing anything off, without declaring an ending, attention can continue to drift, not downward into deeper questions, but inward, towards stillness, carried by the same steady laws that govern stars and particles alike, easing into a state where understanding no longer needs to be active, because the universe continues on its own, quietly consistent whether observed or not.